it gives you a good indication of the learning points that would be useful for you to understand at examination time. Okay? That's all I'm going to say. Okay? Right, okay. So we need participation in the class as we go through this, as always, yeah? So I'll be asking questions, and if nobody answers any questions, I'm going to keep asking them until somebody does, okay?
Yeah.
So I don't want to be just standing here all the time, yeah? Okay, so we started with this diagram at the beginning last week about the integrity management process. And if you're getting sick of the sight of that, then that's a good point, because you should be seeing it lots, because this is the one diagram you need to have in your head to understand the concept of integrity management, pipeline integrity management. Okay? Whichever pipeline system you work operating anywhere in the world, whatever the product is, how its integrity is managed can be aligned to this diagram. Okay? So just think, remember, this is very important. So I had the whole process from start, and I'm not going to go through every stage because I went through a lot last week. But remember, we had the first stage, which was segmentation. Sorry, I'll just get through that in a second. The goal of integrity management, pipeline integrity management, yeah? We spoke about this last week, and what we're trying to prevent are those diagrams, or those photographs on the slide there. And I think there's a couple of people in the class maybe who weren't last week, but some of those are quite famous incidents. The one second on the right is a location called Carlsbad in New Mexico. Occurred about 2001. So there are big consequences associated with all of those incidents, either consequences for people, for the environment, for the buildings, or society in general. Okay, but that's what we're trying to prevent. So whenever you get lost in the concept or the process of integrity management and asset management, and you start to wonder exactly what is the objective of it all, ultimately this is it. It's integrity management and preventing these sorts of events occurring. Okay? We spoke about, remember last time, or I did I guess, about codes, how manage risk. Important points to understand here. It is implicit in codes that they manage risk. So it's not explicit. In a code doesn't say this is how we manage risk. It's implicit. So it's inferred. Okay? So when pipeline codes tell you you need to bury the pipeline at a certain depth, you need to have a certain wall thickness, you need to have a certain design factor stress level, what it is inferring is keep the manage the risk and manage it low and keep it reasonable. Keep populations away from the pipeline, that's what all codes do. Do it slightly different ways, but they keep high populations away from the pipeline. So what they are doing is they are limiting the consequences of a pipeline event occurring, failing, and what the consequences would be. So it keeps people away, it reduces the stress level down. Remember our little balloon concept I spoke about? Leak versus rupture? Remember? Difference between leak and rupture? Huge difference. When you have a pipeline in the future, and you have to be, if you're in the unfortunate position where it's been damaged and it may fail, one of the very first questions you need to ask, what is the stress level in the pipeline? If the stress level is below 30%, if it fails it will leak. Not good, but not bad. If it's above 30% SMYS, it could be rupturing, and that is very bad, huge consequence. So how you manage that pipeline incident is huge different, okay? And codes identify stress levels to mitigate the risk. And the codes invoke inspection and surveillance regimes, flying the pipeline, walking the pipeline, CP checks, etc., etc. And all of that is mitigating the chance of somebody damaging your pipeline, which then causes a consequence of a failure, and it causes casualties, environmental damage, etc. So that's how codes manage risks. Again, I won't go these points in different, but remember there's two prima facie evidence that codes best in the world for addressing these issues, managing system integrity, or API 1160 and B31.8S. And B31 is an ASME document, remember? Everyone knows what ASME stands for? Hopefully, yeah, great, yeah. You see it lots and lots, and it's a good professional body for mechanical engineers. So gas pipelines, B318S, liquid lines 1160, and they have the fundamental rules of integrity management of pipelines. If you're ever involved in integrity management in the future, you will definitely be using one or both of those documents as a reference. Even if wherever you are in the world you do something slightly different to meet government requirements, they will be based on the principles of those two documents. Okay? We talk about segment identification. Remember, at the first stage of the process, can you remember a couple of principles on segment identification? What would we use? Rules? How would we generally segment a pipeline, for example?
Geography.
Geography, yeah. Valve 5 points, pig traps, changes in fundamental parameters such as wall thickness, grade, diameter, that sort of thing. And that's one of the first steps in the integrity management process, remember, segmentation of the pipeline system. Yeah. So we talked about that quite a bit. We talked about risk analysis then, the three different concepts. Simple to the left, very hard on the right. Yeah. Our qualitative, very simple approach. Remember, that was our 5 pipelines on the diagram, where we had small diameter, small wall thickness, that's low risk, high diameter, high pressure, thin wall, that's high risk. So simple risk ranking techniques. Then we have the index or the semi-quantified approach in the middle, and then the full quantified on the end, or 4, not 5. So this is our example. Remember, we went through this last week, so I won't go through it again. It allows you to risk rank the relative risk of different pipelines in your operating company. And a lot of companies do this to identify which pipelines are the highest risk elements of the system in total. Therefore, they are the ones that you use time and money to measure and quantify the risk in those pipelines more accurately. If they're very low risk, you don't need to quantify the risk. So what? If it's high risk, you do need to quantify it. Yeah. So that's our simple method. Remember, qualitative. Qualitative being opposite to quantified. Sorry. So then we had our semi-quantified. Remember, in the middle, where we come up with these sorts of graphs that I won't go through it again, obviously. But the semi-quantified approach allows us to put different factors. So we have a semi-quantification of the integrity of the pipeline, applying different point scoring for the quality of the coating system, the effectiveness of the CP, ground stability, these sorts of factors, and then we'll come up with these very nice flashy charts on the screen there, risk ranking pipelines with a numerical number associated, semi-quantified, so they're not absolute numbers, but they're semi-quantified. So it's a halfway stage between simple risk ranking and very complex quantified analysis. So that's our middle method. We then get to the very complex quantified approach, which is generally for high hazardous locations. So nuclear industry uses this sort of approach. Pipeline operators use it where their pipelines come close to very high populated areas. For example, they would use a quantified approach to demonstrate that the risks they're exposing to the public is acceptable, or a LARP. Everyone remember what a LARP is? A-L-A-R-P? As low as reasonably practicable. Yep, and it's a good concept and one just to have in your mind to remember. So that's a quantified approach. Acceptability risk, I went through this, lots of different levels of judging risk, its acceptability, and you can see a green line, a horizontal line on the chart there, typically for a pipeline where it is. So pipelines in relative terms are generally low risk in comparison to many other activities in everyday life under their industries as well. We then get on to the baseline assessment, which is the assessment right at the beginning, assessing mapping the system, understanding its risks, the integrity issues, etc., etc. Again, I won't go into detail. And then we'll have the Code of Federal Regulations in the US, CFR 195, which is for liquid lines, CFR 192 is for gas pipelines. So we went through, so we did the segmentation, we did threat identification, assessing risk, baseline plan, and then into integrity plans. And now we're up to the integrity assessment stage, which is on the red part of the diagram there at the 3 o'clock position. Okay, so that's very recap from last week. Anyone have any immediate questions on any of that? Everyone okay? Yeah? Good, good. Right, okay, so that's a recap. So this presentation follows on from that one, so I'll run it for maybe about an hour, and then if we'll have a 15-minute break, and then I'll do the video when everyone comes back, and then I'll close out the presentation and any kind of final questions, etc. So that's okay. So what we're going to talk about now is integrity assessment and pipeline life assessment. It's a continued challenge for all operators because and anybody idea what age the oldest pipelines in the world are? Does anyone have a guess? Let's have some guessing. 60s. Anybody think there aren't any pipelines as old as that, or do they think it's older? Anyone? Any older? Anyone going to go back in time? Oh, so you're going to, we're on 100, are we? So 1910s, maybe? Yeah, so we're in the century. Anyone going into the 19th century? Anyone going into the 19th century, or we're not going that far back, yeah? We'll keep out the 1800s, yeah. In terms of gas and petroleum products, then we would. Yeah, if we went far enough and back in time, I think the first nation to use pipe systems as such were the Chinese. I think about 1000 BC or something like that, but that doesn't really count because it wasn't what we're interested in. It was like for water and stuff like that. But the oldest pipelines in the world are generally in USA, around 1920s, 1930s, that sort of vintage area. If you ever look at pipeline networks around the world, and if you look at the USA, you'll see huge intensity of pipelines around Texas and the southern states, Louisiana, etc. And that's where a lot of it was really started originally, where they struck oil 100 years ago. And that's where the oldest ones are. So if you imagine if you've got a pipeline that was commissioned in 1925, let's for example, then trying to understand how that can meet current standards with design and how it would have been constructed, obviously major challenges, and a lot of them have been decommissioned. But there are pipelines still running though, built not long after that. In the 1940s, after the Second World War, there was a huge expansion in the US, and there was in the UK to a degree as well. So there's a lot of pipelines which are 70 odd year old, which were built using materials that wouldn't be used nowadays and welded, not how it would be done today. But they're still operation. They maybe got £1,000 per square inch, 70 bar or whatever in them. So how do you assess the life of those sorts of pipelines? So you've had it been operating a pipeline for X years. How long can you operate it for? What's the typical life of a pipeline? So I'm gonna every single table I just want one number. Okay, so you'll have to agree between yourselves as to 2 or 3 years. So what is a typical and maximum pipeline life? Okay, so we'll start at the front. What do you say? How many? 10 year, 20, 300 year, 2,000 years? What do you reckon?
50.
50, 50. Yeah. So we've got 50 at the front here. Next table, please. 50? No, you've got to have a different one. That's one of the conditions. You can't say an answer anyone else has said, okay? 60. Okay. I thought you were going to say 51, maybe, or 49. Okay. 50, 60. Next table, please. Sorry? 30. Okay, we've got 30, 50, 60. Okay, it's good to be easy to remember so far. Okay, next one.
Average should be between 50 and 70.
50 and 70. Okay, interesting. Yeah.
0 and a billion.
Okay, so 50, 70, yeah. The table at the back, please.
25, 30.
25 to 30. So that's the shortest one so far, but okay, that's fine, yeah. Next table, please.
55.
55, okay, just splitting the difference, yeah. You guys are doing some mathematical calculation trying to cover the bets here, aren't you? Yeah. Next table, please.
Yeah. 60.
60's been said, you can't have 60.
51.
Yeah, no, I've said 51, so you can't.
52.
52, yeah, good lad. Next table, please.
No limits.
No limit. Oh wow, yeah, we've got a risk guy here. No limit. Yeah, it's good. Okay, so I accept your point, but can you just give us a number, please?
50.
50. Yeah. Okay, I'll get you off because he did give us another number. Yeah. All right. Concept anyway. It's an interesting debate, and countries, operators, and governments around the world debate this issue because it is quite a complex issue because it depends what is the limiting factor on the design of your pipeline. And if you want to spend enough money on your pipeline, then it's infinite. It's the gentleman's answer here. It may be costing you hundreds of millions per year, but it just keeps going on and on and on. So once when the sun eventually dies and the earth stops revolving, there's going to be bits of steel left in the earth. You know, they'll just go on forever, but we won't be here anyway. Sorry to be a bit sad for a moment, but the steel will go on and it will go on forever. The issue is there is an optimum commercial life of pipelines, and that's the key point. You can have an integrity life and a commercial point, etc. But to put some proper numbers on it, obviously, because it wasn't just a stupid question, but pipelines are typically designed around 40 or 50 years life, because generally reservoirs would be depleted over that part of time. So if your reservoir's gone, then you don't need the pipeline anyway, so what? But some pipelines that are transporting gas or products within country, such as pipelines quite near Newcastle, go around Newcastle, and gas will be used in the UK for 200 years' time. The question is, will the pipelines who are currently transporting that gas, will they be doing it in 200 years' time? Or will they need to be replaced after 80 years or 120? And that's when you get into the interesting discussions. So notionally you would have typically 40 to 50 years, but the figures that I've seen, generally how long pipelines run before they get decommissioned, it's nearer to 80 or 90. That's general data that I've seen. It's nearer 100. There is a spare, I'm going to comment and talk about a distribution, and that's reality. So there's a lot of complex about design life of pipelines and how you assess the life of it and how long it goes on for. Okay, and that's some of the concepts that we're going to talk about this morning. So we're going to talk about the use of ILI data and how you predict the life of a pipeline. I think, have you had your presentation on inline inspection yet?
Yes.
Yeah. Was that on actually data as well? Corrosion data, yeah. Metal loss data, metal loss, MFL, that sort of thing? Yeah. Okay. So we'll just build on some of that. Yeah. Great. And then, so understand what integrity decisions are taken based on what information you have to determine what's the integrity now. And then it's easy to say what the integrity is today, but what's the integrity of the pipeline going to be on April the 18th in 2028? Okay, that's just a random date I picked, by the way. But predicting the integrity in the future is a lot harder than the now, obviously. So you can look at your car, you can go under the car, you can lift the hood on the bonnet, you can look at the engine, you can do bits of servicing, and you can say, today my car's okay. It's getting me from A to B, no problem. But what's it going to be like in 15 years' time? Degradation, that gets a lot more difficult to judge. And that is what operators spend billions of dollars or whatever currency a year trying to predict. What their system is degrading at and what rate. Because that determines what they spend regarding CapEx and OpEx. Has anyone not heard the term CapEx and OpEx before? It's very important to operating companies. Okay? CapEx is capital expenditure, OpEx is operating expenditure. Okay? So when an operator is operating a system, they are always balancing CapEx versus OpEx. How much do we keep spend maintaining this pipeline on the OpEx, or do we get a point where it's not worth it, let's replace it? And that's the CapEx argument that kicks in. So operators, whoever you work for, they will be into CapEx, OpEx decisions, because it's all the financial modelling of the company and how they maximise. Because remember, what operators are after is They want to operate safe pipelines, yes, but what they're looking to do is to maximise the return for whoever owns the pipeline, whether that's the government, shareholders or whatever. They want to maximise the return. So they want the optimum capex, opex. And that sounds a bit cynical and capitalist, I suppose, but that is the world we live in, unfortunately. Okay, so that's a reality, if anybody didn't realise that. And how we integrate the information together, I'll get onto as well. Okay, so we're going to go into integrity assessment, which is the, as I say, the red part of the diagram there. So we need to, before we start trying to predict what the integrity is going to be in the future, assessing the life, we need to currently understand it now. It's obviously, we spoke about inline inspections, so there's tools, techniques available for measuring defects in the pipeline and categorizing it, sizing it, its significance, that sort of thing. So there's techniques, tools available, and there's above ground teaks, there's lots of different techniques available. We select based on pipeline attributes such as wall thickness, grade or whatever, and inline inspection. I'm not going to talk about too much inline inspection because you've got other presentations on it, but inline inspection techniques cover a whole range of different technologies and physics phenomena, from ultrasonics to magnetic flux fields, acoustic resonance fields. There's all sorts of clever physics that are used on inline inspection tools, and you use them depending on what you want to or look for, what you're looking for. Yeah, if you're looking for cracks or what are sometimes called planar defects, you need certain types of tools. If you're looking for general metal loss, which is corrosion, gouges, you have a different technique. For dents as well, if you want to size dents, slightly different technologies. So it depends what you consider as a threat, and then you assign the technology to the threat and you use the technology, and that's what you do. So in terms of techniques, we've got inline inspection. I've done the first one there. The second technique is pressure testing, is understanding the integrity. So has anyone ever done any pressure testing or know anything about it? Yeah. So what different types of pressure testing can you do?
Hydrotest, pneumatic.
Yeah, some good answers there. So hydro, which is water, obviously, good old the water that we love, you know, H2O. So we use water. We also use pneumatic testing, and pneumatic purely means with air, so it may be nitrogen, or it may be the good old air that we've got out there, you know, the 70% nitrogen and whatever the hell it else makes up, I can't remember. I just remember nitrogen's the most. Or it could be any other variable to that. Or it could be product testing. So whatever product you've got in the line, you could use that to pressure the test. Yeah, and you would use those for different reasons. For example, yeah, why? What's attractive for using water as a pressure test? Using water as a medium for pressure testing. Why would you use water?
It's readily available.
Sorry?
It's readily available.
Well, it isn't in the Sahara, and it isn't on the top of the Andes. You know, it is, yeah, because you're in England and we've got billions of gallons of it, yeah. So it's no problem for us, but it is generally available, yeah. Not always, and it is usually the first option to use. But if it's not readily available, that's another issue. Why would you do pneumatic testing? So with compressed air or nitrogen, for example, why would you demonstrate the integrity with pneumatically rather than hydrostatically? Sorry? Yeah. If we're looking, that's right. So when we were talking about using H2O for a test, that's a strength test. That's checking the integrity, the strength of the system. The gentleman at the back was talking about using a helium trace in an air, and that's for a leak test. So if you want to check about leaks at flanges, etc., what they do is they'll put a helium trace in the gas that they have in there, and they'll have helium detectors around the site, and they will pick up. So that's a type of test for leakage, but not really integrity. Okay, it's not for integrity per se. But some people will do high pressure pneumatic pressure tests. Well, why would they do that? And what's the dangers associated with it? What do you think? Why would they do it? Why wouldn't they why should they not just use water? Other than if they haven't got any around, there's another reason as well.
Because they want to operate that particular pipeline at that pressure.
Yeah.
And they want to see will it withstand
To withstand it. And the big drawback of using water is you've got to get it all out of there. And you've got to dry it, and you've got to find it somewhere. So, depending on where you are, you may be able to dump it in the nearest lake if you can get away with it, but you shouldn't do that, but some people do. Or you need to take it into tanks and get it disposed, etc. So it can be difficult to dispose. And then you need to dry the pipeline as well from a gas point of view. It's a big cost associated. But so it has huge drawbacks using water, but it has one enormous benefit amongst any other medium for why people use it. What is the huge benefit of hybrid testing?
There are no long-running cracks. I mean, in case of failure, crack won't propagate because it depressurizes.
Yeah, it won't go as far, that's for sure. So there's that's one of the complex reasons why it is used. The fundamental use it is used because it is almost uncompressible as a fluid. Yeah. So if you raise a cubic meter of water by 100 bar, you won't add a lot of fluid to it. I can't work it out at the moment, but you won't need to add a lot of fluid, a couple of litres maybe, because it's very incompressible. And what that means is it doesn't have a lot of stored energy. Yeah. So whether a rupture occurs or if a fitting comes off by accident, and it happens, then there is less stored energy gets released. And what happens with energy systems is when it's at pressure, it's got its potential energy, and it transfers into kinetic energy if something goes wrong. What kinetic energy is half mv squared, so that energy transfers into the projectile that it's going to throw off. And if you just do a Google search on hybrid test failures and fatalities, you'll find quite a few on the internet. A lot of people get killed every year, and that's pure using water as a medium. But it will have the stored energy of perhaps 7/100th of for gas pneumatically. So that's why hybrid testing is used a lot. Even though it's difficult to get out, etc., it's the simplest way to prove it and safest to prove integrity. So once you're doing air testing or product testing, if it's a gas, then you're getting into a lot more difficult area. So to demonstrate the integrity, you would have to expose the public at quite a high risk while you do that test. So that would need to be taken in the company. Pipelines normally are strength tested using water, okay? But installations, because they're complex to bleed, then they'd use pneumatically. Very few pipelines are air tested to prove their integrity. But normally it's because they can't get water, they've got no access. There was a big pipeline across the Andes about 20 years ago into Colombia. That was air tested, and the problem was because it was difficult to hybrid test. Firstly, for getting water up the mountains, but also because the problem with water, because of its hybrid test, because its density, you end up testing very short sections because you have a static head on the pipeline that increases the pressure, which limits what you can test. So quite often, if you hybrid test a pipeline in the future in a mountainous area, you'll find that the pipeline test sections will be very short, because the longer they are, the greater elevation difference in it, which adds to the pressure, which makes it more dangerous. So because of the mountainous terrain in South America, they ended up air testing it because they're going to have to do too many test sections. So there's different mediums available. So pressure testing is a way to demonstrate integrity, and before the 1970s/80s, that was the main technique that operators used because inline inspection wasn't available. But it was quite difficult because it would involve taking pipelines out of service, and then you had to recommission them, lost the money, downtime production, lots of sort of reasons. So it is used sometimes now, but very, very rare, to be honest. It's mainly the likes of ILI. So that's pressure testing.
Excuse me.
Yeah.
So I would imagine that was done during construction, like before commissioning, testing with water.
Yes.
So during operation, is it possible that they could still use water?
They could do, yeah. I mean, they could do, yeah. Generally, pipelines would always be hydro tested at the beginning after construction, but during the lifetime, if they couldn't use inline inspection, or they couldn't use it to detect the defects they want, then they would hydro test it, because in inline inspection, it doesn't have. Does anyone came across the term POD, probability of detection, before? If you get into inline inspection, you will come across it. It's as it suggests, it's the likelihood of detecting. Inline inspection techniques are not 100% accurate. They're not 100% reliable. Even though inline inspection companies may tell you that in the future, just tell them, when they say that, you just say, I don't believe you. So just say it very politely, so I don't believe you, it won't be 100%. Because they will miss defects and they will have sizing errors. But a pressure test tests everything, absolutely 100%. Okay? So it tests everything fairly obviously in there. So it's a more simple quality assurance for operators in the future. But the reason why it isn't done regularly even now is we do have inline inspection technologies available, and it is very expensive to do hydro testing, as I say. Because if you have, say 50 kilometre pipeline, 600 mil diameter, to inline inspect that could be 150,000, for example. To hydro test it, maybe 500,000, a million perhaps even. Hydro testing is a lot more expensive because you need to take the pipeline out of service and all that sort of thing. Yeah, it just gets more complex. Yeah.
One more question.
Yeah, sure.
In the UK,
Yeah.
for hydro testing, do we use chart recorders?
Chart recorders.
Yeah.
Well,
In the UK.
they will measure the main test parameters. So what they'll measure is the pressure, obviously, from a pressure transmitter. They will also measure the temperature, and also they will measure the volume of the water being pumped in. Okay, so they would put that on chart recorder or a logger, something like that. It's fairly obvious why they would record the pressure, but why would they record the temperature during a pressure test? Why would they do that? Why does it matter? Who cares?
The temperature affects the pressure.
Sorry?
The temperature affects the pressure. So there's a very great fluctuation of temperature.
Yeah, and definitely if a lot of the pipeline is above ground, so it's getting solar gain or it's getting wind chill effects, etc. And if you are trying to determine if the system has full integrity and pressure containment, you test it maybe 24 hours. So you're recording the pressure over a 24-hour period. And what you will see is that the pressure will drop off through the night, and then it will pick up again as the temperature warms up, etc. And you need to determine that is absolutely from just due to temperature, but not because there's a leak somewhere in the pipeline system. So they'll record temperature as standard as well as part of the pressure test. They also record the volume to raise the pressure. Okay, so that's the third thing. And the reason that they've measured the volume is they want to be confident that the material is elastic. Okay, so if you plot a chart, XY graph, so on the x-axis we have volume of fluid added, and on the y-axis pressure raised, then that should be linear. Yeah. So every cubic meter of water added equals 10 bar, for example. Keep the maths simple. So we know that when we've done 6 cubics at 6 bar, etc., and it all goes nice and linear. So that gives them confirmation that the material is responding elastically. Okay. So if they were doing that pressure test and they found that they had to increase the ratio of adding more fluid to get the same pressure increase, what does that mean? So instead of adding, if they had to add 1 cubic meter to get from 5 to 6 bar, but if they added to get 2 cubic meters to get from 61 to 62 bar, assuming that there's no leaks anywhere, so it's all self-contained, What does that tell you about the pipeline? What's happening with the pipeline? Any thought? Yeah, I guess you know the answer, do you? Do you? Or you
Yes,
just
sir.
okay? Go for it then. Yeah.
Plastic decoration.
Yeah, it's going plastic. Yeah, and that does happen if you have what's called rogue material. Yeah. So you're meant to have a yield of 450 megapascals, and you've got a wall thickness of 11.91 millimeters, for example. And all the steel mills provided all that, and you've put it in, and that's all good stuff. But the supplier ended up providing you some 7.1, not just 1191. So most of it's 1191, it's correct, but maybe he's got 20 pipelines in there somewhere that's only 7.1. Okay? So once you start doing your nice pressure test, at some point you will start go beyond the elastic limit, the yield point obviously of the material, and it will start globally plastically deforming and ballooning literally. So it'll be still containing, but it'll be permanently deforming. So by monitoring the volume you're putting in the pressure test during it, you can detect that there is any non-linearities, that's called, in the pressure test. So that's why some people will consider the pressure test is a proof of design. So it's a proof that the combination, that whatever wall thickness and grade material you've got in there is fit for purpose. Okay, so that's why they measure volume going in as well. Yeah. So pressure, volume, and temperature. Okay. Yeah. I digressed a bit there, but pressure testing is important, so it's worth talking about it. And then we have another technique called what's called direct examination and above ground surveys, etc., which is sometimes called direct assessment. Above ground survey techniques, does anybody know what they are? Anybody seen any, ever heard of any? What's an above ground survey technique? Other than the technique above ground, obviously. You can't just rearrange the words, you know. What is it? What is one? Can anyone give an example of one? Sorry?
Patrol.
SIPs, close interval potential surveys, SIPs, or DCVG. Anyone heard any of that? Yeah. They're techniques where people will walk atop the pipeline and they'll have different sensors, and they're looking for voltage gradients between the ground and the pipeline, which will indicate that the pipeline is corroding or the coating is damaged. Okay, so there's several above ground techniques, but that's what they're all generally trying to do, to understand is the pipeline corroding and if the coating is degrading, etc. So that's a collective term for above ground surveys. And those techniques are quite important for one type of pipeline type, which is the one that can't be internally inspected. Okay? Of all the pipelines around the world, there's nowhere near 100% of them can be inline inspected. I don't know how many, maybe 70%, something like that. There's lots of pipelines out there can't be inline inspected. So then you only have this above ground technique. That's all you've got to manage the integrity, and that makes it very difficult. So all things being equal, to manage the integrity of a pipeline that can be internally inspected is a lot more straightforward than a pipeline that can't. So in the future, again, if you become involved in managing pipelines that cannot be inline inspected, you need to treat them very carefully, and they have to be managed very carefully, as I say, because it's a lot more difficult to understand the condition. But why would some pipelines not be picked? Why would they not be done it? Well, why would they not be inspected? I don't know.
Because of joints, valves there, not installed properly.
Yeah, there could be geometry.
Oops.
Yeah, there could be. Yeah, exactly. There could be geometric constraints because inline inspection tools are generally full bore. Not always, but generally though. So maybe 95% of the bore. So if you have reducers in your pipeline, or you have valves which reduce the cross-section area, then that limits the inline inspection's capability. And there's always developments going on in this area, but that's one reason that stops them being inspected. The other point is flow. Okay, inline inspection tools need flow, fairly obviously, but they need quite accurate flow and well controlled. Inline inspection tools don't really handle variable flow very well. It doesn't like it very well. So if your pipeline system has either A, very high flow, or B, very low flow, or C, very variable, that make it more difficult to inspect using inline inspection. Yeah? So it could be how it's constructed, lots of sort of reasons. It could be that the operator doesn't want to do it as well for whatever reasons, because above ground techniques are a lot cheaper, obviously. But typically regulators around the world would prefer inline inspection though. Regulators would normally assume to be the best available technology. So if you're not using inline inspection, I think you need to have a good justification within the company and to the regulator as to why you don't do that. Because regulators usually like operators to use the best state technology that's around the world, yeah. Okay. Equipment inspections. Obviously, we're talking about plant as well. I know we're talking about pipelines all of the time, but we're also talking about installations on the pipeline as well. And installations tend to be a lot more problematic or difficult for operators to manage than pipelines, to be honest. So, does everyone know the type of installations that you'll get on pipeline systems? And give me some examples, types of installations that you have on a pipeline.
Compressor station?
Compressor station for gas, and the equivalent for hydrocarbons is pumping station. Yeah, you get very frequent pumping stations on hydrocarbon systems because of pressure drop, obviously. Yeah, which you guys are all theory analytical guys. I'm sure you know more about pressure drop than I do. There you go. We've got an expert in the front. Everybody wants to know pressure drop. So for hydrocarbon systems, they will have pumping stations maybe every 20 clicks, 30 clicks I've seen before, especially if it's smaller diameter. For small diameters, more drag. Yeah, fluid doesn't like drag, doesn't like friction. Yeah, so we've got pumping stations on liquid systems. Other types of installations?
Metering stations.
Sorry? Metering?
Station.
Yeah. Two types of metering you get. You can get physical metering and product metering as well, so that's another size of installation. What's the biggest installations that you get on pipeline systems? What's the biggest one? Because you haven't got to the biggest one yet. What is the biggest you can get? It may have a compressor station on it. It's that big. What would it be? It may have storage on it as well. It's bigger than that. It may have block valves on it. It may have a compressor station on it. Huge tanks. It could have metering on it as well. Block valves. Could have all of those. What would it be?
Processing unit, refinery.
A refinery? Yeah, it could be. Yeah, it could be. So it's like a refinery or a reception terminal. Yeah. So it depends on what country you are. Well, Nigeria, you have big terminals in Nigeria where the pipeline product hits the land and it does refinement, etc. In the UK, there are huge reception terminals. A place called Bacton, which is northeast of London, in East Anglia. So all of the gas that comes from Russia via Europe and from Norway goes through that reception terminal. So that's an enormous facility, and then it has compression on it before it goes into the grid. And there's another one at a place called St Fergus up in Scotland, which is north of Aberdeen, way even north of here, a couple of 100 miles north of here, right up the east coast of Scotland. So reception terminals and big processing plants are enormous installations, and they're the biggest that you'll ever come across. Yeah, so they're the largest ones that you'll get. Then we'll get with metering and different installations. Okay, so what's the smallest installation that you'll get on a pipeline? So we've done the biggest. What's the littlest? What's the smallest one you can get? Sorry?
Valve station.
Yeah, valve station. A valve. It can't get any easier than that. So it's a block valve. Yeah, with a bridle pipe work. Yeah. So people have a bridle pipe work going around the valve, balance the pressure, so you'll have a standard block valve site. And typically gas operators will have block valves every around 20 to 30 mile. So quite frequent, yeah? And liquid guys could have it even more frequent. So what's the purpose of the block valves being there?
Safety to control flow just for safety purpose.
Yeah, definitely if there's a loss, if there's a product released, then it allows you to isolate and divert product elsewhere, etc. So it's generally used for management of flow, if you like. So if there's an incident downstream, then they'll close the immediate block valve. And quite often these block valves will be remotely operable, so from a main control room, or they'll go on a pressure drop. So if it's meant to be 65 bar downstream, and a transmitter goes back and said it's all of a sudden it's 15 bar, there's something major happen, it slams the valve, and it closes the system down. So that's just a range of installations. Terminals, huge refineries, top of the end. Block valve stations are smallest, and there's a range of ones in between, not just making picking stations and all of that. So equipment inspections are done at all of those types of installations, yeah? So there'll be people using NDT techniques, ultrasonics, magnetic particle inspection, radiography, all those sorts of techniques. So they'll assess the integrity of the fittings and pressure vessels, because some of these pressure vessels could be quite large, their integrity using those sorts of techniques. ROV type inspections is generally fairly obviously for subsea pipelines or for large river crossings as well. So there's river crossings in the UK that are a kilometre across. You know, it's pretty big, and maybe 50, 60, I'll try and keep on method all of the time, maybe 20 metres deep. So how you inspect that, obviously it's difficult, so they'll use ROVs. But the offshore industry, anybody knows a lot about the offshore side? Is anybody? Do we have a Mr. Offshore or Mrs. Offshore in the audience, anybody? Yeah, I mean the likes of ROV technology is used a hell of a lot offshore. Yeah, so accessible for, it's so inaccessible because of the loads, the forces and all of that. So remotely operable vehicles are used quite a lot offshore and on water course crossings, even for onshore pipeline systems. Okay, so there's different ways, different technologies and techniques we have at our disposal as pipeline engineers, but we need to align those technologies or map them to the threats on the pipeline. So you only apply a technology based on appropriate threat. Obviously, you need to be using the right tool to measure the threat that you perceive there is for the pipeline. So 31S, which is, remember, is the ASME document that lists a whole host, of pipeline threats, etc. And we'll just go through them fairly quickly. But first one is third-party damage. So, in terms of third-party damage, I'm sure you've heard that term quite a lot. And does anybody know what first and second-party damage are? So first party is, sorry?
The owner.
The operator, yeah. First party damage is the embarrassing one where the operator has done it themselves. Okay, and that shouldn't really happen ever, but it does. And there's, they'll hit their own pipeline or they'll do whatever. But that's first party damage. Second party damage, what would that be?
The company is allowed to work in the pipeline?
Yeah, a contractor. Yeah. So we have company A at the top, and he employs company B. So he is working under his instruction, the operator, so he's second party, so he's not a random third party. So he should be working on a permitry system, etc., and he causes damage. And then third party is the total external, so it's another utility, or it's somebody doing a development of property or whatever, and he just takes out his JCB and he hits your pipeline, etc., etc. So the people will sometimes call third party damage, or they'll call it external interference, which is a collective term. Yeah. So the collective term external interference will have different sub-causes, and you would mitigate those threats quite differently. Okay. So if you have 100 external interference incidents on your pipeline last year, and 80 of them, and so this is going to be a memory test for all of us here, so 80 of those incidents were first party, 15 were second, and 5 were third party. Okay, so 80 is first party, 15 is second, and 5 is third. Okay, so what are you going to do to your integrity management strategy to address those? Some thoughts? Yeah? Training for who?
For my people.
For your people, yeah. Let's try and knock that 80 down, that's pretty bad, yeah. We'll do some training, you do root cause analysis and all this good stuff, investigation. What about the others? What about the 15 and the 5? What do we do about those? Let's take the 15 first. What do we do about the 15?
We hire more competent contractors.
Yeah.
Investigate and find out whether they were actually
Yeah, so there's
qualified to do the job.
fundamentally you want the contractor to do the job safely that he's meant to be doing, fairly obviously. So there's different aspects you would do. Firstly, you'd ensure that you're appointing competent contractors in the first place. And that should be the case, but it isn't always. Because if you appoint somebody incompetent, it doesn't matter what training after you've lost it, you've lost the plot straight away. So you need to appoint somebody competent, and then you need to monitor them, manage them, and you do what's toolbox talks. Anyone heard that before?
TBT.
Toolbox talks is a bit of a phrase where when a contractor is going to be working on a project, so-called toolbox, they'll have a meeting in the morning and they'll go through exactly the techniques they're going to be using, safety management systems, PPE equipment required, all of that sort of thing. So that's the 15%. So what about the 5% at the end?
Before you leave that, what if there's something like an agreement between the operator and the contractor, like damage anything, take responsibility for it? Is it possible? Or is it
Well, in terms of on the legal side, do you mean?
Yeah, that's something like that.
Well, yeah. I mean, they will quite often get into legal arguments because sometimes the monetary consequences could be huge. But it always gets quite difficult for operators to defend, to be honest, because the likes of the safety regulator will always say that ultimate responsibility is with the operator. So even if they appoint somebody and they get it wrong, normally it will always come back to the operator to that's unfortunate. If you think, remember that small incident in the Gulf of Mexico with BP? There was that 70 billion or something like that. But the main cause of that incident was the drilling company, which were a US company. And they caused, I think they were quite high proportionate on it, but BP ended up with a fine. And they tried to pass some of the costs over to the drilling company, but not many. It's very difficult, to be honest. I think it's difficult when you get into that. You just try and prevent it full stop. But yeah, companies will do it. Yeah, it's difficult. Yeah. So did we get to the third party, the 5? I think, didn't we?
Increase surveillance.
Yeah.
Increase the surveillance.
Yeah. Increase surveillance. Just keep monitoring these activities around the pipeline and how are they getting there. And it depends who they are. Sometimes there may be landowners like farmers, agricultural land. So they have maybe traded ownership of the land over time, and then you've got a new landowner, and he decides this great big field that he's got that looks quite nice, he's going to build something at the end of it because he didn't know the pipeline was there. So operators will spend a lot of time and money to educate landowners where the pipeline is, and if they want to dig anything around there, put drainage in, for example, for agriculture, for crops and all of that, then they inform the operator, and the operator will send somebody out to observe that sort of thing. Yeah. So they challenge the 5%. Yeah.
And maybe putting the signages.
Yeah. And generally, operators will usually have pipeline markers, but they can't get overgrown. The question is whether people read them. That's the problem. Some don't, I suppose. But if we had our data set of 80, 15, 5, I mean, to be honest, the big investigation would be on the 80. So the others people would just put to one side, I think, because if the own company is causing 80% of the damage, there's something fundamental going wrong. But anyway, so that's an idea of, as I say, for third party, etc., etc. Cyclic fatigue to prioritise assessments. Right. So what does that mean? Cyclic fatigue. Does anybody not know what fatigue is, or do we have a fatigue expert who wants to explain to people, and then I'll cross-question. Anybody? Fatigue? Yeah? Because you must go about, you know about fatigue, some of you guys. I'm not gonna, you're not going to be wrong. Well, you may not be, it depends what you say. Yeah. What is fatigue?
It's where failure occurs as a result of dynamic or cyclic loading.
Yeah, dynamic stressing, that's right. So it's stress, dynamic stressing, cycling going on, and the cause of that stress cycle could be anything. So it could be pressure fluctuation or product in the pipeline. If the pipeline is varying 10 bar per day, as it's from high-low demand, then that will be a cyclic hoop stress and longitudinal stress in the pipe wall. And then you get thermally induced cyclic stresses as well, as pipeline systems go through thermal cycles, either through the product temperature varying or the external environment around it. And I was on a pipeline in Saudi Aramco where it used to get 60 degrees in the summer, and then through the night in the winter it would be 5 degrees. And that is an extreme temperature cycle. So if you have a pipeline system that is locked with these block valves, and the temperature is going up and down like that, and fairly obviously we all know that steel has a coefficient of expansion, it wants to get longer. It wants to go in every 3 dimensions, it wants to get longer, it needs to extend. So if it's constrained, what happens to the stresses? They go up. It can't strain, stresses are there, so it gets cycling. So you can get quite complex so-called fatigue cycle stressing of pipeline systems. So the threat is identified in 318S that you analyse the fatigue analysis to determine how the integrity of the asset is deteriorating. And the way in which they do that is the way they correlate or assess fatigue damage is the stress variation and the number of cycles. That's called an SN curve. I don't know if you guys seen that before? Yeah. So it plots stress variation against number of cycles. Yeah. So if you have obviously high stress cycling, low number cycles, could be equivalent to low stress cycling, high number of cycles, but they don't have equal importance or sensitivity, stressing and number cycles. One of them is a cubic effect compared to the other. So does anyone have a guess who doesn't know the answer? So if you know the answer, don't say anything. So which one of either the stress range or the number of cycles is a cubic effect more important than the other one? Stress? Is that a guess or you knew?
No, I saw it while referring for my thesis. S cube n equals one value.
So educated guess then. That's what we'll call that, educated guess. So it is the stress that's cubic. So it is quite important though, because what it means is that if you have a fatigue life of a system and you double the stress range, yeah, then how much have you reduced the fatigue life of the asset? How many reduced it by?
8 times.
Yeah, an 8. That's great. Yeah. And I just kind of like to keep the easy maths because I can do 2 cubed, so I know that you're right. So if you double the stress range, it's an 1/8 of the reduction on the fatigue life. Yeah, and that's quite important so that if you are managing a fatigue issue on your system, you get far better value in changing the stress range rather than the number of cycles. Yeah, because you get far more fatigue life by reducing the stress rather than the trying to modify the number of cycles. So obviously the inverse argument is as well, if you half the stress range you get 8 times the fatigue life. Okay, so it's the way that organisers look at it. But so cyclic fatigue is a specific threat, and it needs to be managed by understanding what rate it's occurring, and then you need inspection techniques to assess what it's doing. Because if you have a pipe material which has no defects in it and is homogeneous, what is the fatigue life of that pipeline? it's what this gentleman's answer right at the beginning. It's forever. It's infinite, yeah? The only thing that has fatigue lives are structures that have stress concentrations or welds. But unfortunately for us, pipelines have both of those. That's why they have a fatigue life, yeah? So what the fatigue what the fatigue mechanism will do is it will grow defects, and that's what it will do in your system. Okay? So if you have very, very small sharp defects in longitudinal seam welds or circumferential, cyclic stresses will grow them. They'll grow them longitudinally and they'll grow them through wall. And then they will get to a certain dimension that they will then fail. And they will either fail as a running fracture, so it's a little bit different to our leak rupture idea. It will run as what's called a running fracture, depending on the toughness of the material. But if the material is very tough, it won't run longitudinally and it'll just go through wall and leak. Yeah? So that's why operators, for older systems where they have lower toughness materials, they need to consider fatigue a lot more in detail than modern operators of modern steel systems, operators. So that's fatigue. Manufacturing and construction defects, so prioritise high risk, blah blah, in terms of what could be there. So manufacturing and construction defects, what would they be? What would they be? Why would there be manufacturing and construction defects there? Why?
In the pipe mill, when it's being manufactured, the right process or the quality of the material.
For the manufacturing, yeah, and it depends on the quality of the mill who provided the material and what the standards were relevant at the time they did it. So there's lots of, and if you think, has anyone ever seen steel production, pipeline steel, and how its pipeline is produced, etc.? And you can get, you'll see, yeah, YouTube, if you want to kind of search YouTube for that sort of thing, you can, you will find something on it. But it is an incredibly complex process. And there's a lot can go wrong with it, obviously. You could have flaws in the starting material, and then you could overstress it doing the Ewing, Owing, and the shaping and the welding. So you can get manufacturing defects in there. And certain line pipe production techniques are more likely to produce certain types of defects. So operators who own pipelines where the steel is produced in a certain way, there's one called HFI, high flux inductors. That's quite difficult, problematic steel where they have problems with. So that's lots of types of manufacturing. So whenever you have a pipeline in the future, don't assume that the pipeline was manufactured correctly and it's defect free. Well, you can assume that, but you'd be wrong. But so I suggest you don't assume it. Construction defect, yeah, sorry, go.
Question about cyclic fatigue. What might be the difference when the cyclic fatigue applied on base metal or on welded joints? So which one fail faster?
Yeah, which one? Yeah, we'll spin a coin, shall we? The answer is that the weld does something else that the parent plate doesn't have. So if you had the same defect in the weld and you have the same defect in the parent plate, the defect in the weld will fail first. And the reason is that because the weld produces a stress concentration. Because the weld is a geometric discontinuity with the shape of it. So you'll typically get a stress concentration, maybe 2 or 3 at the weld. So if you have a cyclic stress in the base metal of say 100 newtons per millimeter squared, or 100 newtons per millimeter squared, but you could be 200 locally at the weld toe. So it's just going to grow the defect a lot quicker, or plaster collapse it, I suppose.
It is overmatched.
It could be, yeah, and also bearing in mind you've got increased hardness there, you've got an HAZ, and that's why most fatigue failures occur at welds, because it's a combination that, you bear in mind with the welding process, what you're doing is you're applying hot molten metal onto an existing material, so there's going to be cooling effects and shrinkage, etc. So every weld in the world, this sounds quite a big generalization, but it is right what I'm about to say. Every weld in the world has got a crack in. Every single one. But the good thing is that most of those are absolutely micro cracks. So they're at like an atomic level structure, like so they're not an issue. But steels have cracks in, they have very micro cracks. They always have, because that's the structure of the material, that's how it is. So as long as it's not below, above a certain threshold size, it won't go and fail. But that's why welds, as I say, are more susceptible to failure, because A, they've generally got more defects in the parent plate, and they're more highly stressed. So it's a bit of a double killer for the welds, if you like. They're more prone to the defect type and they have higher stresses, so yeah. Is that okay? Yeah. So yeah, sure, yeah.
The pipe mill, what we were talking about.
Yeah.
When the pipes come out of the pipe mill,
Yeah.
the suppliers give the test certificates, MTCs.
Yeah.
So there is no guarantee that the test certificates are correct, because if there are defects, then
Yeah, I mean that's right. You need to bear in mind that the test certificate that you're talking about, that the mill has given you, that is a test on 3 mini samples of tensile material, and that could represent a kilometre of pipeline. Okay. Now, if you had one line pipe section, and they're typically 10 metres long, so from here just past that far wall, that will have a huge variation in material properties within it. So whenever you get a test certificate, it's really just, it's an indicative value. That's all it is, to be honest. We'll come into probabilistics a little bit later, in about half an hour. So it is, yeah, you're right. It's just an indication that it's X65 or whatever minimum. It's not guaranteeing it, but it's suggesting generally it will be that level. But it's certainly not telling you what's exactly in every single line pipe section, because they're highly variable. Yeah. Okay. Is it okay for that? Okay. So the last one's probably the main one for most operators around the world, which is corrosion. So segmenting pipeline systems to understand the risk of corrosion to them, such as different coating types, because you may have different coating types on the pipeline, and some coating types will degrade a lot quicker than others. So the likes of fusion bonded epoxy, that's quite a high quality one, but you can get simpler type coal tar enamel techniques, which have far more limited shelf life or operational life, deteriorate quicker, etc. So operators will take into account the type of coating as a pipeline threat, because it may degrade quicker than other types of coatings in other sections along the pipeline. So it allows to help into this segmentation, but corrosion obviously is a fairly major threat for most operators. So we did a little bit on the integrity assessment and different techniques. But we'll now just go into discovery management. So we can use all different techniques to identify features, defects, cracks, corrosion, dents or whatever. And then the question is, well, what do you do about it? You found it, so what do you do next? And that's this discovery management element. So we need rules for once you find a feature, a defect or whatever. How do you manage the whole process of how assessing its significance, and how do you move forward for it, if you like. So operators will have prescriptive rules, for example, such that if defects are above a certain size, they will just repair them immediately. Okay, and you've got there typically 50%. So for example, if you find corrosion half the wall thickness, then the operator may, in their management procedure, is they would repair that automatically. But if we've got a 10mm wall thickness pipe that is 900mm diameter, and you find 5mm deep corrosion in there, which is, let's say it's this long by that, if you like, so that by that, is that an immediate integrity threat to that pipeline system, do you think? Or for you to make that decision, what questions would you ask me? So if I'm the person in the trench, I've got my mobile phone here, and you want to ask me, what else do you want to know from me? So it's 5mm deep, it's about this long, that wide if you like. What other information do you want to understand how to assess its integrity?
Direction, the shape.
Yeah, direction, so longitudinal or circumferential. Yeah. Well, why is that quite important? Why?
So like the type of
The stress is in the two direction. Is it the high stress in the two direction?
Well, stresses are in all directions, obviously, but in terms of principal stresses, you get in thin wall structures you get 2 principal stresses. Thick wall structures you get 3-dimensional principal stresses. But for pipelines, the 2-dimensional stress fields predominantly, because it's so thin, you don't get stress variation through wall. So the principal stresses are hoop or circumferential and longitudinal. And obviously, depending on how the pipeline is constrained at the end, then the hoop stress will either be twice times the longitudinal, yeah, or the longitudinal will be 0.3 Poisson's ratio effect. So if we have this defect we were talking about, if we have it in the circumferential direction, that is a lot less of an integrity threat than our longitudinal orientated one. Yep. Any other questions anybody would ask me? Because I've still got my phone here in the trench, Well, what else do you want to know? Yeah. Because I'm leaving in an hour, so you haven't got long. So what next? Because I'm having a coffee break in a minute. So what do you think?
The distribution and then how distributed.
Did we ask about
Any other features around there?
the
Yeah.
location? You can ask location, for example, close to girth weld.
Yeah, exactly. Where it is relative to a girth weld. If it runs across a girth weld, is that good or bad? That's bad. That's very bad. Yeah, that's not just bad. That's very bad. Yeah, going across a girth weld is very bad because it's going through a structure that we already know has small cracks in and has a stress concentration, has a heat affected zone, etc., etc. So we want to understand anything around the defect that changes one of 2 parameters, yeah? Because defects fail because of load resistance combinations. Okay? When load increases resistance, defects fail. So when I'm in my trench and you're phoning me and speaking to me, you want to understand anything that changes your understanding of the load on the defect or the resistance of the defect. Okay? So the load on the defect is changed because it goes across the weld. Yeah? And it goes because it's longitudinal rather than circumferential. It changes the load across the weld. The other aspects could change the load on it is if there is settled ground settlement going on as well, overburden loading. So that could be an additional load on top of the stress caused by the internal pressure. Yeah. So any of that would change. So that's all load related. The other part of the equation is the resistance. So the resistance of the defect to the load, that is predominantly due to the shape and the size and the dimensions of the defect. So if we have this nice shape here, this shape and deep, so what we want to know is, what is its profile? Does it have a sharp bottom on it? Or is it flat bottomed or curved? Is it all smoothed? Or does it have cracks within it? All of that sort of thing. So and there's lots of procedures around that will take you through all of that. But it is quite it's quite a difficult assessment to do, because there's lots of factors that you want to understand, that anything that changes your view of assessing the defect, because you need to do a fitness for purpose on the defect, which I'm not in to talk about today about that, but when people do fitness for purpose assessments, what they're doing is they're identifying what the failure pressure is of that defect, and therefore what its safety margin is. So if your pipeline is running at 70 bar and somebody calculates that they've got all the information in and they say its failure pressure is 77 bar, so that's 10%. Is that, does that change your view to anything on the defect? Do you think it's reasonable to have a 10% safety margin? Is that sufficient for somebody to be in the trench working away? Yeah. Anybody think it is a good enough safety margin? Yeah. Anyone come up with an argument? I mean, you can't come up with arguments. I suppose it depends why. Any circumstances why it would be okay to have just a 10% margin, because it doesn't seem a lot, does it? Obviously, it's. I suppose if you had a lot of conservatisms in the assessment that you did, assuming material properties a lot lower than the actual, something like that, you can. But typically safety margins would be higher than that, maybe 40-50%, something like that. Yeah. So that's why they'll get all the information on site, defect sizing and all of that, just so somebody somewhere, because typically this person's on the end of a phone somewhere, and they need to get, and it is difficult, and I've done this before, we're speaking to people on site and they're saying they've got pipeline damage, and the options are either A, do I close the pipeline down, which is $500,000 a day, or do they do a repair, which is $500,000, or they do nothing, or they walk away and backfill it, you know, big decisions. So all of this discovery management addresses that by allowing you to have proper protocols and procedures for gathering the information on site, so you can analyse it and make the correct decision. Right. Just another 5 minutes, I'll finish this slide and then we'll get a coffee break if that's okay. Predicted failure pressure, which I was just touching on that before, which is our 77 bar, if you like, versus 70 MOP. And then time to failure estimates as well. So if it's a corrosion feature and there aren't other activities going on, then corrosion rates generally tend to be quite low. Does anybody know a typical corrosion rate for a steel? How many millimeters per year would you corrode? 2 mil a year? Yeah. Any up or down on 2? Anyone higher than 2? Anyone higher? I know you got the highest. 2 mil a year, yeah. Oh, you could be higher than that, and lower as well. That's the problem. Yeah.
Are we talking about general corrosion?
Yeah, galvanic corrosion. Yeah, and you will sometimes get quite aggressive corrosion techniques, microbiological, etc., where you can lose several millimeters per year. But typical galvanic cell corrosion, which is what you normally see on pipelines, that would normally be a fraction of a millimeter per year. So maybe 0.1 mil, something like that, 0.2. So if you guessed that, you guessed right. Or you knew, then congratulations. But predicting corrosion rates is really difficult. We'll come on to it after the break. But it's important to operators what rate their system is corroding, so that they can understand how much do they need to spend to maintain it, and then when do they replace it in the future. So predicting asset life. And they do that using probabilistic analysis, which I'll do in the next slide. Defects can grow by corrosion or by fatigue, so they're time-dependent mechanisms, obviously. Corrosion has a time-dependent mechanism in that it is X millimeters per year it's growing at, and then sharp features grow by fatigue at X millimeters per year as well. So if you have a crack in the weld, you can't predict at what rate it is growing length and depth. per year, if you like. So it'll allow the fitness for purpose analyst to predict how long it will take for it to get to a failure condition. So the various assessment methods, and if you read 31S, then it'll go through this. There's different assessment methods for all those different defects types, and the assessment methods are quite different. So metal loss defects are the defects that you'll come across more than any others, and they generally are just a simple corrosion, and they use the likes of what's called B31G, which is an appendix to ASME 31, and they use an advanced technique called R-streng that I won't get into it at the moment, but there's lots of experimental tests have done over the years failing corroded defects and then working back empirically based on the theoretical data what the safety factors are. So lots of tests have done failing actual and artificial metal loss features and then come up with rules for how to assess and predict at what pressure a defect would fail at. So that's for metal loss features. Dents do potentially two things to the pipeline that we don't want it to do. First of all, we have this geometry discontinuity. So the pipeline's sitting there quite happily as a thin tube under the ground, which is the perfect shape for resistant pressure. Then a dent is there, and that causes a discontinuity, and that what causes is stress concentrations. Yeah. So the stress isn't predicted anymore more by PD over T. You get a big concentration in the dent because of the profile. So if you've got a defect in there, it may be subject to 2 or 3 times the stress that the main pipeline is in. So that's one thing that dent is. And also, whoever dented the pipeline, they did work hardening on the surface, so they created a hard layer and potentially more cracking, because hard materials are more susceptible to cracking. So there's two things. It causes a hard layer, potential crack, and a stress concentration. Gouges, similar in metal loss defects in that it's a reduction in the pipe wall, but again gouges have this hard layer produced due to the impact of the indenter as well, so it's more complex to assess. And then dent gouge combinations, I'll come right at the end. Then we have cracks, which are sharp features, sidewall or lack of sidewall fusion in a girth weld, just material separation as it starts to go into fatigue. And then laminations, laminations are produced during the steel manufacturing process, so they're layered separation layers within the pipe wall while the material was being rolled and manufactured. So there's 3 or 6 defect groups there. So just as the last exercise just before we break for 15 minutes. So if we number these, number 1 top left and bottom right is laminations as 6. So 1, 2, 3, 4, 5, 6. Okay. I'm going to give everybody 30 seconds only. When every table I want to agree in 30 seconds, so it's a nice challenge. I want you to list 1 to 6 in terms of least severe and maximum severe. Okay? And there's lots of variables and you'll have lots of questions, but you've got to just run with it, I'm afraid, without that. So which type of defect is the least significant and which is the most? So metal loss is 1, dent is 2, gouge 3, 4, 5, 6.
Depends what kind of depends what size of the crack. How was the press? They're very small. A lot. It's 5. That is very bad. Shall we say that for them?
What is more sensitive to them for a
Okay, guys, everyone, I think given the time, I'm just thinking maybe why don't we have a 15-minute break now, and then we'll compare results straight after the break. Okay, so you're going to have 15 minutes if you want to talk and come to a final conclusion. There's no prize at the end, by the way, but let's see. Okay, okay, I'll see everyone in 15 minutes if that's okay. Yeah.
Based on the number.
Yeah, we're going to go Friday. Right. Answer. But I mean, Friday we're going to match. I didn't even No, but I didn't know that until I went yesterday. That not because I went back last night and I realised that's the same person as me. That's at half and I thought, I'll just say it is and it wasn't. She's too tall.
What is
Okay, see you like I accept
1, 2, 3, 4, 5, 6, 7, First one is 4. Towards integrity, just integrity. Okay.
no, right starts. Okay, 1 second. One crack happened. In 5 seconds, can the pipe be explode? But yeah, so in the case of dent, it can. Yes, not immediately, but 5 seconds is more than enough. But it still depends if it's a big, it's a intense crack. Yeah, but if it's an intense crack, yeah, you do the actually cracks.
How could you be very good at this?
We're having lunch and one came to my place.
Have you been at a cold talk? No, no, it just says Spanish, but I don't.
Where you are, where you are, man, you're not single, man. You cannot be more than here. He's not single anymore.
What? It's not even that. It was just generally that. Different area.
Yeah, that's the
I knew what was it.
No.
Right.
No,
The ground survey.
Yeah.
You mentioned some
Techniques. Yeah. DCVG, which is direct current variable gradient, voltage gradient, sorry, and SIPS, CIPS, close interval potential survey. Yeah. They're the two main techniques.
The manufacturer of the pipe mill.
Yeah.
They stamp the heat numbers.
They will do on the certificate. Yeah. So
And when it also on the pipe, some manufacturers stamp. When I was working in Middle East, I've seen that.
yeah, just on the inside,
Exactly.
they'll have heat number with
exactly,
a pipe number sometimes.
Right.
Yeah.
So when we are laying our pipes, we see that it is missing.
All right. Okay.
And in such case, there is nobody to take a decision.
Yeah.
But as per the procedure, it's in the procedure on the codes that it needs to be stamped.
It would normally be stamped, yeah,
So
because
if it is missing, how would we react?
I mean, you would. The simplest thing to do would be just to reject it, it's whether it's likely to be a rogue piece of line pipe or not. It's probably, it would seem by what you've explained there, it's just a case of they just forgot to stamp it. So maybe get somebody from the mill to come over and to do some tests on it, inspections, and then they can stamp it there, I think. Yeah, so there should be an overall certificate for the batch number anyway. So the fact that it hasn't been marked, I've seen it sometimes they haven't. Sometimes they don't always mark them anyway, to be honest. You know, or they'll stamp on the end hard. You know, on the weld prep, you would stamp it sometimes with an indenter. But typically they'll just have a painted stencil, which I guess you saw. So it's when that information is missing. The problem is that people will think that the worst case is that it's maybe some rogue material and it's not suitable or whatever. You know, which. But then, where do you get a pipe from? Pipe section to replace it. You know, you're stuck onto. You know? So I think you get the mill out there to recertify it in situ, and just to say we'll stamp it, and then get some compensation from it.
Because I had experienced this in my work site, so that's why I came up with
Whereabouts was it in the Middle East?
in the Middle East,
Whereabouts?
in Qatar.
Qatar, okay. I've never been
I was
there.
working for Qatar Petroleum.
Oh, yeah.
They are a national company.
Alright.
I was there for Saudi Aramco also.
Yeah.
My experience is I work on refineries, unit piping, pipe racks.
Yeah.
So I have come from that background.
Okay.
And the second interest is I was working on hair liquids. Hair liquids, one company.
Okay.
They had a new installation, a 6-inch pipe.
Yeah.
And it needed to be pneumatic tested with nitrogen.
Okay.
So it was 25 bar.
25 bar, okay.
25 bar. So it was like it's dangerous to do at 25 bar with nitrogen. But in the cases if client emphasizes that this needs to be done, so we have to do it. Even if the code says that it's at such high pressure.
And you can't do those tests safely, but you just need to have safety precautions in place, the likes of exclusion zones. Because typically if you were doing a pipeline pressure test to 100 bar or so, your exclusion zone during the test would be maybe 50 meters, 100 meters. But for a pneumatic test like that, it may be 400 meters, something like that. Big. You know, I mean, we used to do. I used to do a lot of failure tests, pneumatics, and where small fittings, valves, can go 400 meters. So they're all rules. They're all guidance notes on how to calculate what's called hazard distances, hazard zones for the projectiles. They can be quite big. It depends on what volume you're pressurizing. But if it's an installation where you may have maybe 10 cubic meters volume, that's a huge. If you work out the stored energy, yeah, you're into like megajoules. You know, it's big, and all that energy gets converted into some fitting. So it transfers over, so it's then half mv squared, and how far it goes, you know, some distance. Yeah, so it's you've got to be careful with pressure testing. Yeah, there's been a lot of really bad incidents over the years. There was one in the Middle East the year before last. I think it was in Saudi Arabia. The one where a couple of guys died. You need to be careful. They just don't realise the risks. You know, they don't manage them. That's the client
pressurize the pump.
I've seen it. I was out training there for about 6 years. I used to go out 6 weeks and do 6 weeks training. You know, like this stuff for 6 weeks, you know, with one of the guys. I mean, I must have trained probably about 400 or 500 Aramco engineers, you know, so that was quite interesting, you know. But, it's a different country, that's for sure. Yeah.
They are state of the art.
Oh yeah, no problem. Right, okay. Right, shall we, let me see how that goes. Right, let's try and start to fill these numbers in, shall we? So, which, any full tables here. Do you want to, have you decided, you two guys? Use that table 6, 8, aren't you? Is that right one? Is that, we've got 8 tables, 1, 2, 3, 4, 5, 6, 7, 8. Right, so use we'll call use table number 8, so you're the last one. So right, so what's your 1 to 6? Which numbers, what order, yeah?
6 first, I mean the most severe first, right?
No, less severe first.
Less severe.
Yeah, so least to worst, yeah?
Least to worst, okay. Least to worst, least to worst.
Least is first is lamination.
6.
Right. Do you want to shout the numbers out, because I'm typing here as well. So 6, yeah?
1,
yeah,
3,
yeah,
2,
yeah,
5,
5.
4.
Okay, thanks. So we'll talk about them at the end. Next table, table 7.
Well, sorry, we basically picked the top one, the list. Our imagination was.
Okay.
Picking 2.
Yeah.
So the list was still lamination.
Right, so you want to just shout the numbers out just so I can type them in
The
here?
list is lamination.
6.
6.
And then the worst, not the worst. We didn't put
So you just did the top and bottom?
Yeah.
Okay.
Yeah.
Okay.
Crack was the lowest.
5.
Okay, that's number 5, yeah? Okay, that's what you mean there, yeah? Yeah, okay. Okay, next table. Number 6, yeah? The least severe to the most severe, yeah?
The most severe lamination.
Okay, so that's 6, yeah, okay. Do you want to just shout the numbers, yeah? Which one? What number?
3.
3. Okay.
The most
2, yeah. Next one. 1. 4, yeah.
I think they're all the same.
One.
It depends on the extent of each one. The less
There must be 5. There must be 5 because that's the only one left. Yeah.
For me, they're all bad.
Okay. That's great, thanks. Okay, next table at the back there, please.
So remember we are equal for
Yeah.
Just say the top and bottom.
1, yeah.
The most of it is correct.
1,
Yeah.
2, did you say?
Yeah.
Yeah.
6 lowest.
6, yeah.
6.
3,
say
5,
Okay, say that. 5 is the most.
that's 4. Yeah.
Did you say that if it should be linked?
Good stuff, great. 6 or 4. So let's
Meta was again.
so let's go back to table 1 now.
Yeah, yeah.
Okay, so table 1.
Say that.
Okay, guys, you've got to make a decision now.
What if they are equal to each other?
You're not allowed to do equal. That's the new rule.
That's right, but the last one is number 1.
Number 1.
And then goes 1, 2, 3, 4.
1, 2, 3, 4.
And 6, 5.
You,
6,
you,
5.
you're not going to go 5, 6 now, are you?
6, 5.
6, 5. You're going to change the last 2. Okay. Okay, great. That's yours there. Yeah. Okay, next table, please. Table 2.
1,
1. Yeah.
6,
1, 6. Yeah.
3,
3,
2, 4, 5.
2, 4, 5. Yeah. Brilliant. Thanks. Okay. Table 3, please.
6,
6.
1, 2, 3.
1, 2, 3. Yeah. 4, 5. Okay, that's great. And the last table at the back. Yeah. Like you're on your own.
Six, 3, 5.
No, because
Right.
that's to be from you.
6, 3, 5. Yeah.
5, 2, 1, 4.
2, 4, 1.
No, 2, 1, 4.
2, 1, 4.
Yeah.
Great. Okay, good stuff. That's quite an interesting exercise, I think. People's decisions, and I'll just talk through them in a second. But the absolute correct order is obviously could be anything because we need a lot more information. A lot of people, but it is useful exercise because quite a few have put laminations in first or second. Yeah, and that makes quite sense because normally laminations are quite innocuous and you get them quite a lot in steel. Most pipelines have them of some degree. They're only a real issue if they've got cracks associated with them. I mean, obviously if the lamination was 3 meters long, I appreciate that would make it quite a severe feature. But as a general, if we're doing like a bit of a qualitative comparison here, aren't we? So lamination, having lamination at quite the top of the pile is makes quite sense. And then number 1, which is general metal loss, and again people have that generally in the first, second or third, and that makes sense as well because general metal loss features have a lot more remaining strength than sharp defects like as gouges, cracks, potentially dents as well. Yeah, so general metal loss features are the simplest you can get of any feature, so it makes sense to have metal loss number 1 there as well. And then just looking at, if we take 2 and 3, 4 collectively, so I know I may be confused the number at the beginning, but number 2 is dents, 3 is gouges, and 4 is dent gouge combinations. Okay? So 2 is dents, 3 is gouges, 4 is dent gouges combinations. So all things being equal, 4 should always be higher than 3 and 2, because the dent gouge combination does a couple of things. It does about 5 things. You have a dent in there that changes the stress. You have a hardened area at the bottom of the dent. You then have a metal loss in there, which is corrosion, which could have cracking in it as well. Okay? So of 2, 3, 4, 4 would be the worst of the 3 of those. And then between 2 and 3, dent gouges, you could have them either way, to be honest. It depends how big the gouge is and how big the dent is. And then the only one I haven't covered is 5, which is cracks. And again, it's quite different to all of the features, to be honest. And cracks, because they're very difficult to measure and to determine their integrity, it's a lot easier to assess the integrity of a gouge, metal loss, or a dent, etc., than, again, everything being equal, which is quite a caveat statement, I would say cracks are the worst of the lot, from my point of view. But if somebody wants to argue one of the others is higher, I'm quite happy, because I could come up with other defects in the other groups that would be worse than a crack. But all I would say is an absolute simple rule. And I say that there isn't a perfect answer, but all I would say is my suggestion, based on balancing everything, I personally would, and I mean, who am I? You know, I'm just giving my view, but I would say personally, I would say 5 first, then I would have 4, then 3, 2, 1, 6. So 5, 4, 3, 2, 1, 6. So I don't know who got the closest to that.
We got it spot on.
Yeah, you got written it down there. Yeah, sure. There's quite a few who are really close to it, to be honest, because 1, 2, 3 are quite close together anyway in reality. So I think, I don't know, there's a couple of tables. I think a couple of tables there got it pretty close to it. So it's a bit of an interesting exercise, just how you look at these features. What I'm saying is that there's a big range of defect types. There's a huge range of dimensions of all those defects, and then how they could be important to the pipeline's integrity would vary on a lot of other factors as well. Its depth of cover, its pressure, all that sort of stuff. But yeah, so just final my kind of view for whatever that counts for, I would go 5, 4, 2, 3, 1, 6. But it's just a thing about how to look at these things, yeah. Okay, is everyone happy with that little exercise of participation? Okay, good stuff. Defect assessment is a huge, massive, complex area, and you may never come up with it again, but you may see reports of other people doing these assessments, and as I say, they're incredible complex analysis, but it's just to appreciate it. So in the life assessment, there is a whole process on discovery management, which is all about these defects when you find them, and invariably operators need to compare different defect types. Which ones do you repair first and which one you don't? And they go through decisions and discussions exactly what we've had on the 6, trying to compare different, not just same defect types, because that's quite easy. You've got 30% corrosion and 50%, all things being equal, it's obvious. When you have different defect types, it gets a lot more complex. Right, okay, so that's discovery management. And then we get into the actual significance of the features. Is that readable at the back and everything? Is that okay? Yeah. So what we've got here, XY plot, x-axis, we have, this is an example of an inline inspection run, for example. So on the x-axis we have the defect length of the metal loss feature, so it's a bit of corrosion, and then we have the depth of it on the y-axis, from 0 to 100% theoretical. So there's a whole plethora or a whole range of actual corrosion features are plotted on here. So they're combinations of how long it is and how deep it is. Nothing about width, if you notice, but we're not particularly interested on width, because these are longitudinal orientated where the hoop stress is perpendicular, so it's mainly length and depth that we're interested in. So what inline inspection companies and operators will plot all of this data onto this type of graph to enable them to take decisions. What do they do with all of these features? And if it's a nice pipeline system which has a dry product, inhibitors, etc., it will have no features. But then if it's a very aggressive product, H2S internally or something, you could have 10,000 features. So operators need to have find a way of managing them. So what they do is they they'll plot it, and then they'll plot against these types of curves against them to allow them to make decisions to be made. So there's two lines plotting on there, and what it's identifying is that anything above the very top curve, then theoretically the defect should have failed. That means it may not have done, for whatever reason that the inline inspection hasn't sized the defect correctly. You will sometimes see defects across that failure zone, i.e. they should have failed but they're there. But what the presentation is saying, or the slide is presenting, is that they're ones that were failed already, or you definitely need to repair. And then it has a, so that curve there is calculated from ASME B31G, which determines the defect limit of the diameter length combinations for the pipeline's MAOP. And it then applies a safety factor on here beneath that MOP, draw the line again, and so if our safety margin is 30%, for example, then the second line is plotted. So what it's saying is that from a pipeline operator and an integrity manager, we are happy with a 30% safety factor. Therefore, any features which are below that line, we're not interested about repairing. We don't see them as an immediate threat. But any above, all of these ones in here, then we would actually be repairing them. So just the point here is that because this line here, this safety factor one, that's drawing a line whereby if the defect was in the pipeline at the time of hydro test when the pipeline was built, it would have survived. So that initial hydro test is drawing up a line to say this is the acceptable integrity of the pipeline. So if you have any features later on in the pipeline's life that would have survived that test, the argument is that that defect is therefore acceptable. It's not reducing or impairing the integrity of the pipeline. Okay. Before I go to the next slide, any questions on that slide? Yeah.
Yeah, just back on to the peak depth must not exceed 80% wall thickness.
Yeah.
Is that in respect to the pressure, or?
It's irrespective, to be honest. It's an ASME requirement that ASME B31 states that you cannot have defects deeper than 80% irrespective of pressure. Yeah. So you need to repair it automatically. Now, even if from an integrity point of view you could justify defects deeper than that, and you could, if the defect was quite short, then you could have quite deep defects, because you can have, if you have maybe just a 5 millimeter long defect, that could be 90% deep and it still wouldn't fail. But the 80% is a judgment cut-off that ASME have made to say, regardless of what you say from a fitness for purpose, you shouldn't be having defects deeper than 80%. And I think that's a reasonable good rule, to be honest, because normally operators would be repairing defects long before 80% anyway, to be honest. Once you get beyond it, 50% if you like. Is that okay?
Yeah, well, my thinking was that 80% is quite
very deep.
Yeah, it's extreme. So
yeah,
the safety, the pipeline would be compromised if that is the limit.
It would be getting close to compromise, definitely. But you could, as I say, if you did very sophisticated fitness for purpose, you could justify deeper than defects than 80%. But it's, I think they're just trying to establish a simple rule that really you may want to try that, but from a good practice concept, you should be just repairing them, cutting them out, or doing whatever once they get to 80%. Yeah. Okay, so just back on this discovery management a second. So, okay, they can occur immediately at the time of damage, such as like dents obviously could, because dents are caused by external interference, somebody sitting in the pipeline, and quite often major dents will fail instantaneously, because either whoever is operating the machinery or equipment, they'll either puncture the wall thickness straight off and it'll all fail immediately. But typically the likes of fatigue and corrosion, they'll have a time component to them on the pressure cycling side. So we then get into the really hard and clever part of the analysis, which is trying to estimate corrosion growth rates. Okay, and we spoke about it a little bit earlier. What rate will it go? Is it 2 millimeter per year? Is it 1.1 or whatever? And that's obviously a huge variable that's very sensitive, obviously, for the life of the asset. So there's lots of worst cases, and there's lots of models out there in theoretical studies and published papers. So these guys there, De Ward and Williams, who are Dutch and Belgian, they've done a lot of lab tests on corrosion of plate steels, etc., and come up with upper lower confidence bounds for different steels, different ground conditions, and all of that sort of thing. So there's lots of theoretical data to help the operator or the analyst to predict at what rate will the corrosion grow. You can actually look at measuring online, trying to establish what real corrosion rates, what it says weight lock coupons stroke probes. So this is generally for the likes of liquid hydrocarbon lines, so the likes with H2S and that sort of thing, sour gas type system, so very aggressive. So what the operator will do is that they will insert a coupon in the pipeline in the product flow, and they will wait. So and they will keep bringing it out and weighing it over a period of time, and measure the mass, and the reduction in mass obviously is the ions move off the coupon into the product material. So they'd be in this, so they'd be very small, so there would only be gram samples, maybe 20 grams, something like that, and then they would just over a period of time keep weighing it every 3 months, whatever, and then they'd get a predicted corrosion rate for that material, and then they would correlate the corrosion rate of the coupon and try to translate that with the rate that the pipeline would be corroding. This would be internal corrosion, fairly obviously, because it's internal corrosion induced by the product, as opposed to external corrosion, which is as a result of resistivity between the pipeline ground and the pipeline external surface, and water content there as well as a galvanic cell would generate it. But that's on internal corrosion. And then external corrosion rates is the next group of bullet points. And there is definitely no absolute theories out there how to do it, but NACE, which is referenced there, is which is the Corrosion Society in North America. So they've got masses of correlations of data of different rates, because corrosion rate, growth rate, isn't constant during the pipeline's life. Okay, so corrosion rate in its early growth phase is quite low, then it accelerates and then it drops off as the corrosion gets almost through wall. It then starts to create a layer in the corrosion that stops the water getting in, so it plateaus off. So it's not just a linear relationship, so it's quite complex corrosion rates over an asset life, and what rate it would be doing. So even if you did have data at one point of its life being 0.5 mil a year, that doesn't mean it did that last year or it'll do it the following year. It needs to apply a bit of analysis and analytical thinking to it. But the operators do spend huge amounts studying of this, because still corrosion and external interference are the main pipeline threats that operators are usually dealing with, and probably corrosion is the main one. Yeah, that's causing the misuse. So, and that's why they spend a lot of money on it. So correlations with soil corrosivity, which is the resistivity of the soil, different types of soils, clay, granular, all of this sort of thing. So if you have a pipeline going through different soil types, there will be an inherent corrosion rate across different soil types along the pipeline route. So when you do your segmentation that we spoke about last week and earlier today, if it goes through different ground tundra areas, they could have different associated corrosion rates with them along your pipeline route, which again would change how you would manage the integrity of the route, because you could have certain segments are in very aggressive ground conditions, so they are corroding it a lot faster than other sections. So you focus your inspection and surveillance activities more on them segments, if you like, than others. So lots of complexities with corrosion growth rates, as I say, trying to predict. Yes, we know where we are now, and hopefully we do. Where are we going to be in 5 years' time, 10 years' time? And that really is the huge challenge that operators and inline inspection companies have. And it's worth hundreds of millions to the operator to understand that, because they're making big decisions on that. How often do they need to keep repairing the pipeline, or when do they decommission it and build a new one, etc.? And that's why they spend huge amounts of money on it. Okay, so is that okay on estimating corrosion rates, etc.? Right, okay. So just following on a bit that, so we've got from ILI data. Has anyone seen inline inspection data for real? Yeah? Have you seen it outside of here? Have you seen it in a company before? Yeah? And you'll see them, there's a couple of guys are nodding that they've seen it, where they'll have all the different ILI vendors or sellers, if you like. There's GE's out there, General Electrics, there's Rosen, several different outfits out there. They all have slightly different approaches to presenting the data and how they analyse it, etc. But you need to just to understand the difficulty of what they're trying to do, because the inline inspection tools aren't measuring directly defects, sizes, okay? So it's not like if we had a pipe section in here with some corrosion and we get a rule or whatever and we can measure it, that's direct measurement. But what the inline inspection companies are, they're using changes in physics to interpret what defect sizes are. Okay, and you'll have heard from the ILI presentation if you've had all of it yet. But they're doing things like they're putting a flux field through the wall, and they're trying to correlate a flux field distorting to what it means for a defect. Or they're sending an ultrasonic through the wall, or they're bouncing a high frequency signal through the material, bouncing it and bringing it back, and trying to work out the speed of that signal coming back and how it's changed the profile of it, the amplitude, and what that means, what it means for a defect. So what they're doing is incredibly difficult, which is why it isn't an absolute science. So they come back with masses of raw electrical signal data into their systems, and they do huge amounts of post-processing to try to translate that for us to mean something understandable, such as all of that analysis means this defect, etc. So they'll get raw data like this sort of diagram here, where you've got all spurious indications of defects and lengths and stop positions, lengths and depth information, etc. And then they'll start to draw boxes around defects and try to group them together and categorize them, and do very smart algorithms that they were spending lots of money on every year in R&D to try and improve it and to develop it further. Because these inline inspection tools have multiple sensors on them, so what they're trying to do is correlate different sensor readings to get an overall picture. Because there's a couple of sensors pass a defect, they have 2 bits of information at any point in time. How do you pull it together, and do you make a conclusion as to what it means, etc. So it's just how doing multiple runs with inline inspection just allows the operators to quantify. In 2005 we had this corrosion profile on the pipeline, now we have this one, and so the overall corrosion growth rate is whatever it is. which could be quite variable along the pipeline, but allows them to understand what that is and they try to calculate what it is. So these are types of defects, that, issues that they get regarding drawing boxes around defects and all of this sort of thing. So, and one of the difficulties with using ILI data is the technology has improved massively in the last 10 years, and it did a hell of a lot for the 10 years before that as well. So the problem that operators have, which you'll see at some point probably, when you use a basic ILI tool or a lower technology from 10 years ago, then you use a high-tech tool now, how do you compare the two data sets to understand what's happening with the corrosion rate? And that causes monumental issues for operators. Even if they stay with the same vendor to do the inspection with the same company, trying to understand how the pipeline is degrading between two runs. So how do they box off corrosion features and then size them, etc. And it's just a continued problem to try to come up with real quantified information to understand what the corrosion is now, but how do you compare with what it was 5 years ago or whatever. And then even more difficult, what it's going to be like in 5 years' time, which is the growth rate, corrosion growth rate issue to get into. Yeah, sure, yeah.
How would you deal with a situation where the vendor has come in with new technologies for running the tool,
yeah,
and maybe you did you scanned your pipeline maybe 10 years ago, and now using old technology,
yeah,
so you've now advanced after 10 years,
yeah,
you're moving to the new technology.
yeah,
But remember, there is that marketing aspect that is associated with vendors.
yeah,
So the new technology would cost you more,
yeah,
but also the integrity of the data would be at question.
yeah.
So how would you deal with such a situation?
I think it's a lot simpler if it's the same vendor. So if you had the same vendor in 05 and you've done an inspection this year, it's a lot simpler for the same vendor because they can get back to the raw data from 2005 and almost compare the raw data and to predict what's happening. So they still have a bit of uncertainty with it. I'm not saying it is totally straightforward, but the more difficult situation is if the operator changes vendors, and that happens quite a lot, because then the high tech or the higher tech inspection that's just been done, those guys don't have the raw data from the old one. They just have the basic report, which could be quite bland. It could say there's 7 features, there they are, and they're the dimensions. So that comparison by the new inspection company is going to be at a far more higher level, because they'd only compare those exactly features, wouldn't they, whether it's 7 for example, but they'll not be able to compare with a general corrosion state of the pipeline because they won't have that raw data. Do you know what I mean? So changing vendors, it's a more simplistic comparison, a more difficult one to be honest. But the vendors are all switched onto it because they're all in competition with each other. So if you speak to them, they'll say they can do it to a degree because they are used to re-inspecting lines when another vendor inspected it previously. So they are getting smarter at doing it, to be honest. But I think it's just another complexity in the comparison. You're right, you know. But as I say, if you have the same vendor, you've got a reasonable chance, I think, of a good comparison. And because at least you'll be able to compare the biggest features anyway, because the previous inspection should have found the biggest features. But what you may not be able to compare is all the thousands of really very small features. So it's a higher level simplistic comparison, I think. Yeah. Okay. Okay, so this is just an idea of which is the point you were just asking actually, about old data, new data, and we've got the data set here where we've got a certain corrosion feature that's identified. and it changes in shape. I mean, it doesn't show much change here, but what the ILI company is doing is they're trying to find common features on the previous run that they can compare with theirs, and that allows them to calibrate the new data, if you like. Yeah, so they're looking for matching points across. This is what this is doing, so that they can then analyse other features that have been identified perhaps in the first run. So they try to correlate data points, but just bear in mind they are trying to match electronic signal data, not real feature data. That's the difficulty. So it's incredibly difficult to do, but they're getting better and better at it every year. Okay, and then we get into all of the funds of probabilistic analysis. So we'll go from deterministic to probabilistic. I don't know if people are, I don't know, some of you guys might have done probabilistic and structural analysis. I don't know if you are into that side of it, but obviously deterministic analysis is purely looking at, I know what this metal loss feature is. It's 25 millimeters long, 6 millimeters wide, 8 millimeters deep, and I know what the material grade, blah blah. And the deterministic is that they're all fixed inputs in the analysis, so they're not variables. Okay, you have 100% confidence on all of those data points, so you're not going to apply any variability to it. But what the probabilistic type approach is that it has a level of uncertainty over the reading. Okay, because bearing in mind the reading they're giving you isn't absolute. It may appear an absolute value, but there's a variability associated with it. So for example, they may have high confidence on the length, but for a given defect it has a variation in depth associated with it. So if you imagine those two vertical arrows there, or vertical lines, they're potentially, for a single defect, it could be any depth in that range. Okay, so the probabilistic analysis would do multiple analyses of single features and identify how much significance is it on the defect changing size, and does it importantly cross that red line or not. Because if the significance of a given defect size, its tolerance, changes from here to here, for example, that goes into the so what category. It doesn't matter, it's very safe anyway. The issue is if you have a single defect measurement near to this line, but then if you apply the tolerance error on the reading and it takes it over the red line, you then need to repair it. So that's what the probabilistic analysis will do. It'll determine how many defects would cross over that line that you may need to repair. So it looks at variables of all the inputs in the calculation from a probability point of view rather than a deterministic. So what it'll do, the probabilistic analysis, is it will apply variability on all of the inputs that goes into the calculation for assessing the fitness for purpose of the defect, and it uses what's called Monte Carlo simulation. Anybody do that or heard of it? Or just just like the casino in the south of France, Monaco, and yeah, that's the place. So all it is Monte Carlo simulation is full probabilistic. So what it's doing is millions of permutations of data points together, and it runs them in a random simulator, Monte Carlo type simulator. So it will use all of the variable values for each of the parameters, and then it will come up with a probability of a defect failing or not based on all of the variability of the inputs. So it will have a distribution for wall thickness, because if we have a standard wall thickness of say 12.7, that's a deterministic value. Yeah, is the actual value going to be exactly 12.7? Do you think? What do you reckon? What do you think it would be? What the thinnest do you think you would expect if it was 12.7 nominal? How thin do you think it would go underneath that?
Half millimeter.
About a half mil. Yeah. So you think, so if it's 12.7, it could be 12.2 maybe? You could go down that, yeah. And then in terms of thickness on the other way, how much over possibly? Yeah, you tend not to get less variability over because the supply line pipe from weight, so they try to keep it down. But typically, tolerances on line pipe on wall thickness is around 5%. Okay, so for your 12.7, then in theory the minimum wall thickness should be no less than 5% less than that, which is what? So that's 6.6, is it? Whatever it is, I can't do it with my head on. My son's giving us a headache, I think. Anyway, 5% off 12.7. You guys are all smart. You can work it out. So what the Monte Carlo simulation will do, it will have a distribution of wall thicknesses between minus 95% and 100% of the value. We'll have a Poisson distribution that will apply to the analysis. Diameter is less of an issue, but yield strength varies quite a lot. It's quite important and it's quite useful to us. So if you have a X65 steel, API 5LX X65, so that has a nominal SMYS of 450 megapascals. If you looked at all of the material certs, what sort of yield strength would you actually get? Or what would the mean one, do you think? Min, max and mean, for example. So low point, mid point, max point. What do you reckon?
I think the measure usage would be higher normally because usually in the distribution that the mills provide, they use the lower yield strength.
Which it should always be above because SMYS by its name is minimum. You know, the M is minimum. So it should be 450. So there should be nothing below 450 and everything above 450. Yeah? And that's not the reality, unfortunately, because there's a tail of a distribution that goes below 450. So just if you have, in the future, if you come across an X whatever graded pipe, don't assume that the material, all the material in that pipeline meets that grade, because it won't, because they've got distributions associated with them. Generally, as a rule of thumb, the average mean yield strength of line pipe steels is normally around 10% above SMYS. Okay, so if you've got your certified X65 450, in reality, if you looked at all the material test certs and plotted it all up, you'd come up with near a 480, 490 newtons per millimeter squared. And that's really useful down the operating life of the asset if you need to do defect assessment and all that sort of stuff. But what this simulation does, which is what we're talking about, will have applied distributions to that on yield strength, and it's the same for UTS as well. So it applies probabilities. I don't know how much you use to stats or anything like that, but it'll apply what's called probability density functions to it. So describe that variation. So that's two of the inputs into the assessment, yield strength and UTS. But the modelling will also apply distributions to sizing tolerance. So different defects will have a certain plus or minus size tolerance, and then a corrosion rate on it as well. So if you think, my head's starting to hurt just thinking about all of that, but because you've got in effect at least 10 variables that have distributions associated with them. So if you fix all the values of all those 10 variables, if you fix a single, you do one equation, you do one calculation, and it tells you my defect is this and it will fail in 6 years. And that's a deterministic calculation. But this will do hundreds of thousands of those calculations, and if you think the output of all of that is that it'll fail anywhere between 8 and 100 years with a distribution associated with it. Yeah? So that's what it's doing, which is really powerful from an integrity assessment point of view if you have masses of features, of ILI features, and trying to determine the significance of them, not just now and what will be in X years' time. And that's just a bit of it on the philosophy of this probabilistic approach, and comes up with this concept of probability density function. And as I say, it all comes down to load and resistance, which I mentioned ages ago. So the resistance of the defect to failure is based on its dimensions. Its XYZ dimensions, so its local XYZ axis, if you like, and its defect type. The loading that it's subjected to is based on the pressure that's applied, which is a variable, and then if the thickness varies, then the stresses vary, so that affects the loads. Yeah. So what all of the simulation does is it plots this for every defect that you've got over a whole variable operating conditions, and it plots, well, these are the loads applied to the defects and the pipeline in total, all of the resistance collectively, and then whenever there are occurrences where the loading exceeds the defect size, then the defect fails, obviously. So the percentage, if you see that area under that curve, those two curves where they overlap, that's a measure of the likelihood of a failure, okay? So the probability of it failing is that area divided by the other areas, the total areas, yeah? And that's where these calculations do. They come up with probabilities of likelihoods. So is it 1 in 5,000, 10,000, whatever. So if these two curves massively overlap, there's 90% failure, for example. The way it's drawn there, it would be, I don't know, 5%, maybe something a little bit less. So that's the whole probabilistic approach of assessing defects. And then that previous graph was just day zero now, and then what we then do is simulation, in that we grow it over time as well. So you can see the three plots there. So after different time durations, we see that a shift of the distribution as it grows. So the defects are getting longer, they're getting deeper, and they're changing at different rates as well. So it's another probability or variable, if you like, in the analysis. And what does that end up with? All of that, millions of calculations that have been done, come up with something like this. Okay. Remember, I was saying just before that we did a deterministic assessment on one defect, then we come up with a single value. Yeah, it's going to fail after 8 years. But what the probabilistic analysis does, it comes out with a whole profile against probability of occurrence failing. Yeah. So if you imagine the likelihood of it failing today is 0, because it hasn't, and we've got the data there. The likelihood of it failing in 10,000 years has got to be 100%, and it's how to get from those 2 points, if you like. And that's why it follows this profile here, if you like. So in this period, initially for the asset to create, then it starts to grow, and the increase in probability doesn't increase very much because they're growing. The defects are still quite shallow, and then it has this midlife area where it's fairly linear-ish, and then it starts to accelerate at the end and then turns off. So if the operators are doing an analysis of using ILI data to predict future life of their asset, this is the sort of analysis that they would do, which is incredibly complex, which is really the principles for you to understand, if you like. And then, so the previous slide comes up with probabilities of failure, but the question is that acceptable or isn't it? What's the target level of probability that's acceptable or not? So where is the line when something is acceptable or not? And typically for DNV issue a lot of rules for this for offshore that's used onshore. So they have simple rules about probabilities for acceptability of failure. So they'll higher likelihood of occurrences if there's no human activity around, in that they're more tolerant to a failure occurring fairly obviously if there's nobody around, but if there are people around then it's 10 to the minus 5. So you can then back calculate on here as to where you are on that line, and therefore how long it will take you to get to the unacceptable position. So this then calculates the remaining life. So your risk level is here, and you're going to be growing, and you're going to get to this point when you hit an unacceptable risk level, and how long it gets you from A to B, how long it takes. So a lot of that's quite detailed on the discovery side, but it was particularly, as I say, relevant on the ILI data, using data, probabilistic, looking at the defect geometry, its size, and the material properties, applying distributions to all of those inputs, and then probabilistically calculating the future life by applying a growth rate to it. Okay? So I've got another 10 minutes of talking here, and then I'll put the video on. So we then get into response times with repair, which is on the, whatever colour that is, I don't know. And I think somebody else, I think did Will Sharman maybe talk to you about repair, I think. Or somebody spoke to you about repair, yeah. So I won't go into this too much, but the codes and the regulations, they detail how quickly you need to respond to certain defect types and their sizes, and then what you do. So remember, the CFR is Code of Federal Regulations, yeah? Remember 195 is liquid lines, 192 is gas, yeah? So we have immediate repair when it is required. So for example, if you have a defect that has a burst pressure less than the MOP. So what that's saying is that we found a defect that in our theory we think it would fail below the MAOP. Yeah? So if I go quickly back, so it's up here. Basically that's what it is up there, yeah? And it may not have failed at the moment because you're operating below the MOP, for example. So it may have a 70 bar MAOP, but you're only running at 50 bar, and the predicted failure pressure is 60 bar, for example. So the CFR regs is saying that that requires an immediate repair. Metal loss greater than 80% needs immediate repair, which is your point before about deep defects. It then talks about dents and when they need to be repaired immediately or whether they can repaired later. So they distinguish between the clock position. So dents between 4 and 8 on the top, on the crown, they need to be immediately repaired, but if one's on the bottom half, it suggests are less important. So why would it say that? Why is it interested about the clock position of the dent? So if you've got two dents of the same size, and one of them's found on the 12 o'clock position, and one's on the 6 o'clock, yeah, the back?
On the bottom, it's likely to still be a sprain, is it right? On the top of some sprain.
Yeah, that's right. I mean, it's likely that the one at the bottom has probably been part of construction. So when they laid it in the trench, there was a hard spot on the trench. They laid the pipeline and it dented it. So it's highly likely that dent would have been subject to the hybrid test. So unless nothing's changed with the dent, it would still be acceptable. If you've got dents on the top of the pipeline or the top quadrant, maybe between 2 o'clock and 10 o'clock, that top quadrant there, then it's more likely that would have occurred during the operational life. So somebody's hit the pipeline and quite possibly after the hybrid test. Okay? So they could have cracks associated with, etc. So that's why they distinguish between the clock position. And then they have another set of 2 months after. There's another categorization, slightly shallower dents you see here as well. So a 6% category here, 3%, so slightly shallower, but so you've got a long time to repair it. And then you've got within 180 days, so that's 6 months. So what the code is doing is it's assisting in the user of the document to categorize the significance of different defects and when you should repair them, which ones are urgent to repair and which ones you've got more time to do. So if the operator has a couple of hundred features reported from their run, then these types of ideas just allow them to prioritize the important ones first. Yeah.
Does the code speak when there is multiple dents or dent interacts?
Dents within dents, do you mean? Do you mean dents or dents in close proximity?
Yeah, close proximity. One dent and then.
There aren't any rules for dents in association with each other. There are rules for metal loss features for corrosion. So MAR8013L0301 has rules whereby, because dents tend to be isolated, whereas corrosion tends to be clustered together. So the question is, if we have some corrosion here, and we've got corrosion here, here and here, how do we take account of the other corrosion? And does it influence this corrosion or not? So the main question is that corrosion can be isolated and examined on its own because it's not interacting with the others. So there's corrosion rules, or metal loss I should say, within 31G. But for dents, the 10 wouldn't be because they're so complex anyway, to be honest. The assessments are quite complex. And whenever I've seen multiple dents before, they normally tend to be separated quite apart, so they're not adjacent to each other. But if they are close to each other, I think it would just be a straight rate repair or cut out, to be honest. They're quite complex, yeah. Okay. Yeah. Okay, so I won't go through them because it's similar points before. It's just again trying to differentiate between different defects types and how often, how long you've got to repair. And there's different repairs. I'm not going to talk about the repair because I think you've had the chat on it already of welded, epoxy, clog spring. There's a whole plethora of techniques out there. And ultimately pipe replacement. So pipe replacement is mega cost, permanent solution, grinding, very cheap for light damage, superficial damage if you like, composite sleeves and welded sleeves, medium cost, that can repair a lot of range of defects, and then repair clamp or what's called pitcoats that are leak clamps. So that's an epoxy, and somebody else I think has spoke about already, I would guess. That's clog spring. That's a patch which people generally don't use too much, to be honest. Or you grind as well. So once they've got the defect according to this process, you then repair it. Anyone questions on that? Or, I mean, I can't talk about repair, but I think you've heard it already. But so we then got through discovery, repair and mediation, and we then get into prevention and mitigation. So we're in the green section here, so 7 o'clock or whatever. So we're looking to prevent the threats materializing and mitigating the consequence of them, and taking actions to keep it in check. So for example, if internal corrosion has been identified as a dominant threat to the pipeline, then how do we mitigate the likelihood of internal corrosion occurring? On the basis that we can't just stop production, so it's going to be flowing through the pipeline. But we can use inhibitors. Anybody came across inhibitors before? Scavengers, all that sort of thing. So you can put chemicals in the product that reduces the activity of the so-called bugs, chemical bugs that are in the product that are causing the corrosion. So it's a bit analogous to kind of your immune system on your body, if you like. There's corrosive agents in the product that are causing corrosion. So you put inhibitors to neutralize or take out the effect of that. The other thing is to do stream cleaning. And for very aggressive pipelines where there have been real internal corrosion problems, they may clean the pipeline every 3 months. Okay? So they'll swab it with pigs and they'll put cleaning agents in there, and so they'll fully clean it, scrape the internal surface, take out all of the old product, and they'll do that every 3 months if they get wax build up and all these sorts of things. So quite drastic actions. Or if there is corrosion going on, then we can turn up the cathodic protection system, so we can put more current into the pipeline to keep the cathode and anode balanced correctly, so that it doesn't lose ions to the environment. Or you can recoat. So if the sorry.
So a question I got regarding this prevention. If you have high hydrates in the wax formation there, is it irregular, like rating conditions for the cleaning 3 months? Is it regular, like normal operation? Or
It can be if it's quite active.
It's like preventive maintenance activity.
Kind of bit of a mixture of them both, to be honest, because from an operational point of view, you may do cleaning quite often because it restricts flow through the pipeline. Because if the wax gets built up quite quickly, operators will find pressure drops increasing, and all of a sudden you're not pumping 250,000 barrels a day, you're 210, because the bore's reducing. That's simply what it is. So from an operational point of view, they may keep flushing it through over what frequency. So it's perhaps not corroding, but it's just restricting how much money the operator's making, which is very important to them as well. So you might do it for both reasons, and including hydrates, which is built up when you get water in the pipeline and stuff. Creates like an ice slush type substance, Yeah. Is that okay? Yeah. Recoating, if the coating system on the pipeline gets totally shot to bits and the coating starts to degrade, it can get recoated in the field, and this is incredibly expensive, massive, huge cost. Even if the pipeline's above ground, that we talked about last week, I think, if it's buried, it's just even more expensive. But applying coatings in the field are huge cost. So per kilometre, it may cost you over $1 million a kilometre. And the coating that you're putting on isn't as good as the one you can put on in the mill anyway. So operators will bear that in mind, if you like. So it's really drastic action, but sometimes it is done. And then rehabilitation is really more piecemeal, recoating certain sections or replacing pipeline sections in total, if you like. So increased monitoring of what's happening around the pipeline, if it's the likes of external interference, that sort of thing. And training for internal staff. We're talking about our first party, second party idea we're talking about earlier, how to do that. So there's lots of different prevention and mitigations depending on what the threat is. So if it's corrosion, internal corrosion, you're on inhibitors, cleaning, and CP. Protection systems as well, improving them. External corrosion, CP protection systems improvement would help that as well, obviously. And then mitigation going forward, if you like, recoating, rehabilitation, and then that's corrosion related. But then for external interference, increased monitoring, public awareness, all that good stuff. Okay? Yeah. So general risk mitigation of the pipelines, so increasing the wall thickness, and again we spoke that in the first lecture as well, that if you increase the wall thickness, you increase the resistance to external interference, and it buys you more corrosion life, if you like. Even if you've got internal corrosion, you've got a thicker pipe, then obviously it can last you longer as well. And it's this 30% rule that we'll talk about as well. Higher material grade reduces the chance of a rupture. Why would that be? So if we have X52 in our pipeline with whatever pressure and wall thickness it is, it doesn't matter. But if we replaced it with X65, why would that reduce the chance of a rupture? Why? It's got a higher strength, yeah. It's got a higher strength, but why that reduces the chance of a rupture? What causes a rupture? What causes a pressure? What causes the pipeline failure and therefore a rupture? Remember the fundamental parameters that we have?
Resistance and
We have
friction.
pressure, diameter, wall thickness, percentage of SMYS. Yeah? So percentage SMYS, if you increase the grade, percentage SMYS drops. Yeah? So with X52, if you're operating at 50% SMYS, if you increase from X52 to X65, then you will be operating at 52 divided by 65 times 50, which would be 40 something SMYS. And the lower the SMYS, the lower chance of rupture. Yeah? Okay. So if rupture is the real concern, use higher grade material. Deeper burial, again we spoke about that before. Correlation of depth of cover, less likelihood of somebody hitting the pipeline for obvious reasons. Physical protection, put slabs in, concrete slabs or whatever over the pipeline. Many companies will put slabs in key areas near road crossings or heavily built up areas just to make it more difficult for external interference to occur or mitigate it. Or do more surveillance, line walks, flights, helicopter surveillances, etc. All of that sort of thing. There's a very high pressure pipeline goes right through Tokyo. Has anyone been to Tokyo before? Anyone been? Have you? Yeah? Ah, okay. Well, there's a high pressure pipeline goes right into Tokyo, and I haven't been there, but it's quite built up. I gather there's a lot of people live there, I think. And what they do, the operator, they have somebody walking the pipeline every day. Every single day. Well, not the same person, obviously, and probably quite a few people. They walk that pipeline every single day to look if there's anybody working in the vicinity of the pipeline. So it's such high risk, and they don't want to rely on aerial surveillance or drones or whatever. They want somebody on the ground to see anybody does anything before they start doing anything at all. Yeah? And operators use different systems like optical fibre systems on top of the pipeline, all sorts of stuff, monitoring systems, etc., just to mitigate the likelihood of external interference. And improved safety management procedures as well, which is at the bottom there. So if there is a perceived threat or high risk to the pipeline, then one try to reduce the risk or to mitigate it is just to improve safety procedures, put more procedures in place to check, to establish that people can't do things wrong, or human error, if you like. And that's unfortunately, human error is the biggest threat on pipelines, and it's the most uncertain, and it's a difficult one to manage, if you like. So it's just to try and close that one out as well. And then we get into cost benefits of different mitigation techniques. So if we want to reduce the risk on a pipeline section, we can put a concrete slab in, or we can put some thick wall pipe in, or we can just leave it as it is, whatever the inherent risks is. So if we do nothing, we predict we're going to have 2 fatalities every 10 years or whatever, some injuries, some damages, etc. But the point is, important point is, it's a cost-benefit argument here. So you do nothing, you have consequences, monetary costs associated with it. If you spend money on one of these other options up here, that's the negative side of the equation. But the positive side of the equation is you have less consequences and therefore have less penalties, if you like. So the question is, which technique do you use, and do you justify the money? And it depends on what the change in benefits or the increased benefits, if you like. So if you already have a very low risk, there's no point to put thick wall pipe in or slabbing or whatever. But if you have a certain risk level that the costs could be quite high, then do we end up for the 20,000 solution, or we'll go for the 100k solution? You only go for the solution that best maximizes the value for the operator. And this is quite an important concept to get through. It's the cost-benefit justification for risk mitigation. Okay? And this is how the argument goes through. So for the cost-benefit analysis, determine the effects of the mitigation measure. So what is it getting us? How much is it reducing the risk? And what is the monetary value of that? So in the case of slabbing, what would the consequences be without the slabbing, the cost after, and then you compare. And then it becomes a pure financial argument. Do you leave it as it is? Do you use a intermediate cost solution or a high cost solution, or you relay the pipeline or whatever? So these techniques allow operators to justify how much they spend to the board, etc., to manage the risk level. And then just a couple of slides just to finish off, and then I'll quickly put a video clip on. Documentation is critical. Regulators tend to be quite aggressive in terms of documentation and wanting organisations to have electronic documentation systems where they integrate all the information together rather than just having it spread all over, disparate in some system, etc. So trying to get the documentation in one place to have feedback results into the system, keep knowledge in the system so people don't move on, etc. If they do, then information doesn't get lost with them. So electronic documentation systems are an effective part of this process. And then measure the performance of the system, because this is an integrity management system. So the question is, how is it performing? Is it delivering what you want to do? Can it be approved, etc.? So operators will come up with performance measures for how they're doing. Sometimes they'll call things like KPIs, key performance indicators, or safety indicators, something like that. So they'll come up with some metrics to determine their performance so that they can judge if their integrity management system is being effective. So they look at incidence rates, release rates, infringements, encroachments, that sort of thing. And the financial benefit of the integrity system. Is it delivering what it wanted to do, or what should have done, or can they do anything better, improve it, that sort of thing. So if we've got the system in place, but they're still having 10 incidents a year, then quite obviously something isn't going right in the whole process. So if you're measuring performance, then you start the loop again, and then you continue, go through it and refine it and optimize it. So once you've went through all that loop once, the question is, well, how often do you do it again? What frequency? And there is some guidance in CFR 192, which is for gas systems. Typically the same for inline inspection, typically every 10 years for high stress lines, which is above 50%, 15 for lower stress, and very low 20 years, etc. So the regulations are giving guidance to the operator as to what they consider is good practice for how often you would do these major activities like inline inspection. So that would be the starting point for the operator. They could do it more frequent if they wanted, but this is that's the starting point for them. And this is just the 2 slides to finish now. So on historical approaches on data management, as I say, there used to be huge ranges of different paper systems, electronic systems, and all sorts, and data just didn't come together, which was a whole huge problem for operators previously, and it still is quite a challenge with some now, to be honest. Whereas nowadays what's more common is to what's called linear referencing. So all of the pipeline data gets tried to get mapped onto the pipeline one way or the other. So you've got the ILI data, which will internal on the pipeline, which will have a log of the distance along the pipeline, and then any other integrity related data would ideally like to be overlaid that on top of it, either above ground surveys or any segmentation or anything like that. So if you see just on this graphic here, CP readings, etc., and maybe high consequence risk areas you would put on here as well. So if your pipeline happens to go through past a large hospital or a school, and remember we treat hospitals and schools quite differently from a pipeline routing point of view, purely because they're more vulnerable. Okay, so they have more vulnerability. So if a pipeline failure occurs in a hospital, they can't evacuate a hospital with the same speed as would this building, that sort of thing. And schools are the same as well. And prisons are treated the same as well, actually, because they can't naturally flee the prison. Well, generally they can't anyway. So certain types of buildings, they're treated differently because they're less able to act as the general public would. So special locations like that and environmentally sensitive areas perhaps as well could be overlaid on the system as well. And that's the last slide, so which is all about integrating data, etc., and identify key attributes on it, sensitive areas, that sort of thing, mapping integrity data onto it, onto as well. So it's a bit of a kind of rush right at the end there, but I think we've sort of gone through that loop, and you're probably sick of citing it now, I'm pretty sure. So last week we went all the way to integrity management, integrity assessment. We've covered the loop at the bottom, and then it just starts again from the operator's point of view, whatever frequency they run it. So I think when you're going through all of this info afterwards, probably the day before the exam, I'd imagine, something like that, whenever you're doing it, just kind of start with this diagram, understand the individual sectors or segments, understand how they interrelate with each other, yeah, the concept, and then understand risk and the different approaches, the simple to that difficult type, understand those ideas, how to manage corrosion and to predict the life of an asset with corrosion rates, all of that sort of thing. Okay, so I've just got this video to stick on. So before I just stick it on now, does anybody have any final questions on any of this that I've covered? Everyone happy? All crystal clear, right? Yeah? Good. Right, I'm just going to stick this on. I normally just put this in at the end of the lecture because I'm kind of fortunate in a way in that I've worked on pipeline projects when they've been getting built, etc. So you see a lot of that stuff, etc. And obviously there's a lot people don't now, and so you get into pipeline operating companies, or they've come positions and they've never seen a pipeline, and generally you don't see them because they're buried quite obviously. You shouldn't be seeing them anyway. But I think it's quite informative just as an appreciation to understand how they get constructed and what goes on, and it varies a bit around the world. And this is in the UK, so you see grass fields and all that stuff, so it all looks very scenic and beautiful. All of the UK isn't like that obviously, but all very nice. But there's different environments around the world. But the principles of how you construct a pipeline, it's the same the world over pretty much. The detail will change, but the principles, so I'll stick it on. It's got a bit of sound that you may not hear anyway, but it's quite boring, the sound anyway, so I may kind of interject on any of it, so I'll kind of start running. I mean, I appreciate it's just about 12 now, so I'm just going to run it, and then if there's anyone left in the room, I'll keep it running. But when the room's empty, I'll just stop it. It runs for 20 minutes.
Sorry?
Sorry?
Did you say 20 minutes?
Sorry?
You said 20 minutes.
Yeah.
You're not going to say that.
That's okay, yeah. That's your call, it's up to you. I don't know, I've seen it, This is just a bonus anyway, this isn't part of the lecture, so this is... Sorry? You can't, no, because it's confidential. Sorry. It's probably the only thing you can't get on YouTube, but yeah. I'll stick it on anyway and you can take a view on it. So this was about 20 years ago, just when they're building the pipeline in the south of England. It's going to have a bit of explanation in a second. This is just a bit of an intro to it. Kind of just it'll start showing that how the pipeline's laid out, trenched, well the ground level, then it's trenched, and then the pipeline gets laid in there, welded, and then pressure tested and all that sort of thing. And that's a compressor station there.
Is it a manned compressor station?
They're not manned nowadays. They used to be when this was made. No, they won't yet. There isn't sound on it anymore. Into where? Yeah, that was it.
Of only 17 weeks.
You're the man.
The 25 separate operations of the spread encountered the crossing of 31 main roads, 2 major railway routes, and crossed the M11 motorway twice. But despite these many obstacles,
How did you do with that?
they still averaged in excess of 1 kilometre a day for the individual operations.
I'm blaming you.
This we can already see the team's activity in preparing the site.